On. So you should bring up the FP1 document. This is the FP1 exercises here. Yeah. And maybe, let me see what I have here. Drive. Ooh. FP1 starter, FP1 tutorial. Oh, golly. You guys are so quiet. Why are you so quiet? Okay. No one that's front row? Is it working? You can't hear me? Hello, hello? Yeah. That's more like it. That's the Vemba students I know. Okay. Not here yet. Oh, okay. Well, yeah. Look at you guys, so organized. It's just like Zoom screen, right? It's so good to see you guys in person. Yay. Thank you for being here on the weekend. I know it's difficult to get away. Well, maybe not for some people. I don't know. Maybe some people are happy to get away. I don't know. I'm so happy to be here with you guys. And I brought some treat from Hawaii for you guys. Yeah. So we have because it's a long day, so you have snacks for you have Honolulu cookies and I know, yeah. So I'll put it over here. You guys could. I don't know if you want to have some now, but you want to, yeah. So yeah, if you don't know, these are Hawaii Honolulu Cookie Company cookies. They're really good. Yeah, and they have many different flavors. So try one of each. Yeah. And then of course, macadamia nut, right? From Hawaii. Always good. Got chocolate, honey roasted, one of my favorite, and macadamias. Yeah, maybe you want to try some nuts now? Yeah. Right here, pass them out. Yeah. Yeah. Yes.
We are planning after today.
Uh-huh.
All the parts invite you to join the.
That sounds wonderful. Yeah, she's not feeling so good, but if she's feeling okay, well, yeah.
All the favorites Vietnamese food that you like.
I like everything, so except for maybe some things. Yeah, but most everything. Okay, yes, we will. Well, I think we're supposed to end at 4, right? I think we'll be done before that. Okay, yeah, break time. Yeah, good. Okay. Okay, so let's get set up. We have a long day today. Oh, you're waiting for your, okay, good idea. So let's pick up where we left off for FP1. So you should bring up your, do you guys have a shared document? Like, are you sharing this? Yeah, and then, so when we work, what you can do is you can take notes and put into here. Just to let you know, this document is what, this and your workbook will be what you know, Excel workbook is what you'll submit for later when you're ready to submit for credit, right? So you don't feel like it has to be perfect now. Just take notes. And just take notes enough till you feel like you have good understanding of what it is, because we'll use this later, right? So FP1 we use for FP2, and FP2 we use for FP3. So it's, you know, try to get as much as you can, but it doesn't have to be perfect. You don't have to worry about writing it up. And so today, I said in the Discord, our aim is to finish FP1 workshop and then make sure we really understand what we're heading for with forecast project. And then, of course, we're going to do session 7, 8, maybe 9, maybe not. I don't know. Depends. Yeah. I like to go only as fast as you guys want to go, right? If we go, it's okay if we go slow and have better understanding than going fast and no understanding, right? But if we go really slow, I may have to cut things, which you might like, but maybe not so good, because later on you'll go like, darn, I wish I knew that. You know, I wish I did something. So I don't want to cut things if I don't have to. But in this class, it's not so important exactly what you know. It's more important for you to have a good understanding and experience. Because remember, we talked about in session 1, right? We talked about like it's more about communicating, right? And being able to have meaningful and useful statistics, right? Not so much about I know how to do this, I know how to do that, right? It's because you're never going to know how to do everything, and even if you do, you'll forget. Right? So it's more important to have an understanding of the how to do things, like the practice. You know, how do you approach? What's the kind of thinking that you do, and then more importantly, how do you communicate? And I don't know. This is something that was really interesting to me. I learned this a while back. That communicating and being able to communicate is the same thing as thinking. Did you know that? Yeah, because what is thinking? You're talking to yourself, right? Right? So you're talking to yourself. So when you have to communicate to someone else, you are actually thinking, you're analyzing, you're processing, right? Same thing. So some people, you ever wonder, like in school, why do I always have me write so much? Why do I have to write so much, right? It's because that is your thinking. That is the way we, understand things. We communicate to ourselves. We communicate to other people. So That's why in this class, it's much more important to be able to communicate meaningful, usefully, right? And not so much about, I know how to do this, I know how to do that. Or what's this fact, what's that fact? We don't care about that. Especially in the age of AI, right? In the age of AI, all you have to do is ask ChatGPT. It knows a hell of a lot more than you do, right? It's so, and then, right, so ChatGPT also can be, well, it can be useful to help you communicate too, but it's not so good. It makes things sound good, but it doesn't actually think. So that's something important to realize about AI. There's no thought process. There's a bit of what we call reasoning. Like there's like a reasoning model, they call it, but it's very basic. It has nowhere near the kind of reasoning ability that you have. It's very impressive because it sounds good. But if you look closely, you'll see there's no real thought behind it. Very, very basic, stupid stuff. And it makes mistakes like you wouldn't believe. Like, right? I'm of course a big fan of using AI, but using it as a tool to help us communicate better, to think more, right? But it can't do the thinking for us, right? Just never forget that. AI has no judgment. You know, it tries to make things sound like judgment. The way it does judgment is it just tries to find the thing that sort of matches the closest. You know what I mean? It's like, this is the matches the closest. And in any given situation, that is not necessarily the right thing. Yeah. The judgment requires a lot more than just finding something similar, you know, that matches. It requires going beyond that. Yeah. And so in this class, that's what we're always thinking about. We're always trying to go beyond just the facts, just the whatever I see here, and try to make connections, understand like the story of what's going on. And so in our forecasting project, that's why in this class the most important thing is the forecasting project, because the forecasting project is our opportunity to really try to make sense of something and to tell a story where there's no particular answer that's this is right, this is wrong. Yeah. So while you can of course say wrong things, you can't. You could say wrong things, but whatever it is that you're saying, there's no necessarily one that this is the right thing to do, right? And so you have to construct that story that, tells something meaningful, useful, right? Justifiable, right? And then knowing that when what you're doing, there'll always be something kind of wrong about it. There'll always be something wrong about it, but just hopefully right enough that it's useful, right? This is kind of our challenge of the forecasting project, okay? So please understand, with the forecasting project, there's no like assessment for it. Like you have the assessment for session 1, 2, 3. And even those are kind of like, not so right or wrong. But in the forecasting project, you don't have like something to check against. You have to check against yourself. That's it. That's the judgment that you use is what's being worked on here. You're building your skill in communicating and in your judgment of things. So taking in that spirit, you understand this. So we have forecasting project part 1, which we're describing our historical revenue for our company, right? Now, in some sense, this is maybe a little easier in that we're talking about things that already happened, right? And so oftentimes you can check, did that happen? Is this the way it was? And so we're talking more about facts and things like that. You'll see later on in FP2, where we're even in FP1, so we're going to try to do an initial forecast of our company's revenue. So we will talk about what is the future of our next 4 quarters revenue, right? But we're going to base it on just what historically has happened. And so we need to understand the limitations of this and like why this may not be a very useful statistics or analytics to use for whatever purposes you want to use your forecasting for something accompanying decision. So we'll talk about that. In FP2, we're going to start making the transition. We're going to start thinking about like looking at the shortcomings of FP1 for forecasting. We're going to want to try to figure out like how can we make forecasts that are more useful, you know, and meaningful and justifiable, and what that all means in particular. And then third, the last part, FP3, is actually building a model for forecasting and then using it to do the forecasting. So it's kind of the fun part of the class is that we get there. But, you know, along the way, don't expect to be, you know, it's not always easy, okay? That, like anything in real life, yes, real data, real life, it's never a straight line, right? Never a straight line. Always expect there's going to be curves and bumps and problems, and it's never going to be perfect, right? Yeah. So what we aim for, just like in your job, right? You aim for like good enough, isn't that right? You just need to get the job done good enough so that you can move on and make your decisions, do the things you need to do. Okay, so you can kind of think of the forecasting project as your final exam and all the exams in your project, but they don't have like a right or wrong thing. They have more like a quality by which you do them thing, you know, and whether you deliver something that was useful and justifiable, or you didn't, right? Yeah. And so, you know, obviously don't just ask AI to do it for you because it's probably not going to come up with something that's particularly useful, justifiable. But if you guide AI, you could probably have it help you quite a bit. Okay, and so most of the sessions that we work on are all preparations for this. So we'll talk about, you know, everything that we do. You'll see that we're going to actually end up applying in the forecasting project to a limited degree, right? And you know, again, it depends on what it is. So in this class, you're not getting a full class in statistics, right? You're getting an experience, right? So hopefully you'll leave again feeling more confident in using analytics and statistics for things and being able to communicate that more meaningfully and to your benefit, right? That's the idea. So again, nothing to be scared of. We do have a lot of work to do to get to the place we need to get at, and fortunately you don't need to be an expert at everything. Okay, so that's that. So anybody have any questions before we jump back into the FP1 workshop? No? So again, by the end of tomorrow, I know that's really soon, right? End of tomorrow, we plan to have all the sessions done. Yeah, and go FP2 and FP3, right? Now again, the work in terms of like what you submit, you're going to work on that later. So we just have all the basic stuff done, but then afterwards you can revisit, you know, clean it up, fix it, you know, make it more complete, adjust things, right, as you need to, do the assessments, and then submit it. So just so you put plan in your head now, all the work will be due by December 31st, the end of the year. Because what? Last time? Less time. Yeah, you have a little bit less time. So they just finished 2 days ago, right? And so you'll have 4 days less, right? But the harder part is that they got to do things over 4 days, and you have to do things in 2 days. So we'll see how it goes. But you know, I don't know. It'll be fine. Yeah, we'll see. We'll work with it. Yeah, the December 31st date is because apparently you're starting another class January 3rd. Yeah, and so they need to make sure you finish this one first. So just plan for it, okay? That's all I'm saying. And of course, I'll be around to help, not in person, online if you want. Okay, so FP3, we're describing time series data. Please do not hesitate to interrupt, ask questions, whatever you want. It's, you don't have to just sit here and listen. It's a workshop. We're going to work in a shop, yeah? So that means that together, I'll come around. So let's just try to remind ourselves of what we've done. In FP1, the first step into doing our forecast, we want to build a forecast model. So to build a forecast model, we need to understand our time series data, right? So revenue data is data, it's revenue taken over time, right? And as we discussed, time series data has, in describing time series data, it's the same as describing numerical or categorical data. We use distribution characteristics, right? But we have some particular things that may, over time, be different, yeah? So we might look at instead of looking at the average or the mean, right? We might look at the average over time, yes? And we would, maybe does it stay constant or does it change? If it changes, how does it change, right? We might look at the variability over time. Again, is it constant or does it change? If it changes, how does it change, right? Et cetera, right? So we look at the same stuff. Now, in describing our time series data, the particular way of looking at it is, we first think about whether it's stationary or not. And again, that's just the idea is, do these properties, these characteristics like the mean, the variability, the other properties that we might be interested in, are they constant over time or do they change? Simple as that, stationary. So stationary meaning like I'm stationary, I'm staying the same, right? Versus non-stationary. And of course, in our company data, we don't expect it to be stationary, right? In particular, what characteristic do we think is going to change? You guys remember? What distributional characteristic? You could say central tendency, you could say the average, whatever you want. Over time, we think what? Over time, we think our company's revenue will be the same on average? No. On average, we think it will hopefully increase, right? Most companies would like that. Bank of Hawaii, maybe not. Yeah, maybe not, right? But it doesn't matter. It is what it is. The point is, we don't expect it to be stationary. We expect that the trend, which describes sort of the average, right, characteristic over time, we expect it to hopefully increase, maybe decrease. If it's not increasing or decreasing, that's interesting too, right? Yeah. That doesn't mean it's standing still, but it could mean that over this period of time, maybe we had some big increases, but we also had some big decreases, right? And they kind of balanced each other out. Yeah. Again, I don't know. So stationarity, the time series components, remember, are things that we typically look at in a time series as a way to help model what it is. So to describe our time series, we describe the components of the time series, which focus on particular different things. The idea of time series components and time series decomposition means that we can think of the time series as a combination of these, right? And that by looking at all these four things together, that gives a complete description of the time series, right? Yes. You could move up front. Just kidding. I don't right here. No, just kidding. I'm joking. I'm joking. Yeah. So the idea of time series is not difficult, right? It's just a matter of like we're trying to tearing it apart and looking at particular things so that guess what we're going to do later? Take those parts and put them back together again, right? So if we understand all of the different parts, we can make a model for each one of those parts. Having a models are something based on assumptions, right? We make some assumptions about it. But take those, put them back together again, and then we can use that model to do things like forecasting, right? And that's exactly what we're going to do, right? That's exactly what we're going to do. Nothing more complicated than that. So we're going to talk about, I think we talked about the trend already. Yeah, that was the first part. And, again, the trend over time, we're using the linear trend as a way to describe the secular component. Now, again, a model is something you base on assumptions. Those assumptions are not always going to be correct. You can't prove or disprove them, right? All you can do is try to argue that assumptions are reasonable, right? And so I think in this case, in terms of describing the trend, the linear trend is often a reasonable way to describe the trend for the purposes of what you're going to do, right? So reasonable is, of course, relative to what you're using it for, right? So sometimes I get really strong arguments from my Hawaii students, bless them, right? They like to argue that, the trend is not linear. Like, where's Netflix? Who's Netflix? Yeah, you guys are Netflix, right? It doesn't look linear, right? It's like, woo. And so you're like, it's not linear. It's not linear. Look, it's curved, right? And it's like, it doesn't matter. That's not the point, right? The point is not what is the trend. You wouldn't know what the trend is anyways, even just because it looks like it's not linear, doesn't mean that describing it as a linear trend isn't useful, right? Or wrong. Yeah. It just that means that for the things that we're interested in, maybe we don't care about the fact that it has this nonlinear thing. It doesn't matter for us. We only want to know things like what was the average increase over the time period, right? If that's all we want to know, the linear trend is just fine for that. Yeah. If we wanted to know how this increase changed over time, like how does it increase over time more than like how did the increase, then we might use a nonlinear trend, right? But I mean, how often are you going to care about that, right? You might, but in our class, for our purposes, the linear trend is fine. Again, you get the idea of making the assumption for the model. Yeah. And so it's not a matter of right or wrong. It's just what's useful for us. Yes. What's useful for the purposes of what we want to do. So we're going to model linear trend as a secular trend. And then we also looked at the seasonal component. Again, the seasonal component, yet another part of our time series where we look at, instead of looking at like what was the long-term variation over the time period, we're looking at what is the variation in particular time periods. Yes? And in this case, we're looking at quarterly revenue. So we're going to look at what is the variability in quarter one, quarter two, quarter three, or quarter four, right? Yeah. And what we mean by that, of course, is seasonality, is that every quarter four, we might see a higher than average revenue compared to the other quarters, right? Yeah, so we look at seasonality. One way to model seasonality is to look at each quarter average relative to the others. Yeah, and of course, if everybody is the same, quarter 1, 2, 3, 4 is almost the same, then we would not be seeing a seasonal pattern. Again, and the assumption we make is that this is a periodically repeated thing. It's not just over the time period. We make the assumption that this is something that's intrinsic to our data, or our revenue in particular, that it's a property of the of the population. You know, the idea, you know what I mean, that this thing, that every quarter four, what is it, Amazon, right? Every quarter, not Amazon, let's do, who's good, Costco. Every quarter four, right, we see a, right? And that's not because of the data, right? That's because of the nature of the business. Yes, it's the nature of the business. And again, that's an assumption that we make, but it's not an unreasonable assumption because that's the way Costco works. And we, in principle, we know that, right? And in the data, we're just seeing that. We're seeing evidence of that, right? So when we talk about modeling the seasonal component, okay, we don't model it. We already know in principle what we're thinking there. All we're doing is now describing that. Yeah, we're describing that. Like, it would be weird if we didn't see a quarter four increase in Costco's revenue, right? That would be weird. And we want to go look at that. We'd be like, huh, why aren't we getting that? Yeah, because, you know, you should be. Yes, right? And so, again, my blessed Hawaii students always make this mistake. Always. They always look at the seasonal component and they go for some rule. They always want some sort of rule to follow. Do this, do that. That's what seasonality means. The seasonal indices are more than 5%. And they always go, therefore, we see more than 5% season, therefore we have seasonality. And I'm like, no, that's not right. You might be seeing more than 5% seasonality due to just random chance, right? And has nothing to do with seasonality. Or you might be seeing 5%, more than 5% seasonal indices due to some weird thing that happened in that some time period, like during COVID or something like that. Something weird happened, right? So, I mean, no, you don't argue from the data. We talked about that from session 1, right? We don't argue from the data. We use the data as evidence to support our principles, theories, right? Hypotheses and stuff like that. If we can, right? That's the idea. Not the other way around. We don't generate theory from the data. And same with the seasonal component too. So the way that we're choosing to model the seasonal component is, again, we're going to compute these seasonal indices, which are essentially just the averages for each year, you know, for all 4 quarters. And then you just sort of compare the ratios of each quarter in that year. You know, is quarter 4 above or below the average for all of that year, right? And then you look at those ratios over the time period and you look at the average of that. That's going to be the seasonal indice. That's not the only way for us to model seasonality, but I think it's a pretty straightforward one and useful, right? So again, not right or wrong, what's useful, right? What communicates it. And so our job with the seasonal component is to describe the seasonality that we expect to have, right? So Netflix, we don't expect seasonality. So if you saw seasonality there, something that looked like seasonality, you'd be like, that's weird, right? And you would investigate it. You'd be like, huh, you know, I wouldn't change my theory. I would go back and just say, like, why is it different than what we expected? Yeah. Yes. Yes, but it's different. Yeah. Yeah, of course you can. So you can look at categorical data over time, but remember that the distributional characteristics for categorical data might be a little bit different than, you know, like you look at the frequency. You wouldn't look at like the average over time, but you look at the frequency. You might look at the most frequent thing over time, stuff like that. Yeah. Yeah. Yes. Yes. Well, we'll get to that. Yeah, you'll have to hold on to that. That's yeah, because what we're talking about is looking at different variables, you know, for our forecasting. For right now, our job is to just describe our time series. You know, just describe the time series. And you're right, in terms of seasonality, actually seasonality is a categorical property, right? So it's like, you know, quarter one, quarter two, quarter three, quarter four. But the way we study it is we break that up into groups. We have quarter one revenue, quarter two revenue, quarter three revenue, quarter four revenue, and we look at the distributional characteristics between the groups. And that's the way we study it. And then we model that, and then we can use that for forecasting later. If our company has seasonality, we can say we've described how quarter one, two, three, four work in terms of revenue, and we would make the assumption that that repeats itself in the future, yes, which is not ridiculous if in principle you have seasonality, and then we would add that to our forecast, right? We just make sure that we make that seasonal component part of our forecast. It's similar, but for Netflix, you would not use it because you don't have a seasonal component, right? Because you don't have seasonality, so you would not account for it in your forecast. It would be weird if you did, right? Yeah. Okay. The cyclical one is another component, but that's usually for much longer term time series, yeah? And we're only looking at like 7 years, so something more like 10, 20 years, then the cyclical component may become more prevalent. But over a short period of time, the cycle doesn't change that much, and so we don't need to usually look at it. Not for our companies. We're only forecasting for the next year. So if we're forecasting for the next 10 years, well, that might be important, right? But not for here. And then the last thing is the irregular component. And the irregular component consists of those two things. And this is what we're going to work on today. The irregular component is that we have events that something happens over time that affects our revenue. But that something that happened is like it wasn't a known repeated thing. It was, you know, like seasonality, right? It's something that was, you know, unknown or maybe unexpected, right? Like I had a merger with another company, or COVID was something that came in and like affected many companies, right? Or, you know, regulatory changes or something like that, you know, events, stuff that happens that affects our company. And then, of course, there's the other part of it, which is just stuff that happens that we can't explain, right? You know, things that random variation. So, yeah. So the idea is, and then so we're going to work on that today. And then the last part of it is to take these and put them together and use it for making a forecast. And then we'll talk about the quality of that forecast and what it's good for and what it's not good for. Okay, any questions on what we're doing for FP1? So, yes. Two different types of time? Yeah. Yeah. Yes. Right. Okay. So let me answer your question. It's pretty straightforward. A time series is not literally using time. It just means a sequence, right? So when we talk about these time periods, we just call that 1, 2, 3, 4, 5, 6, 7, just whatever the sequence is. That's actually the time series. It's just the order that you put it in. Yeah. So it doesn't matter what you're using. Yeah, you can use that. Now, of course, it becomes a problem if the time periods are irregular. You know, like these are regular time periods, but it means that if sometimes it's longer, sometimes it's shorter, that may be a problem in your analysis if you just order it 1, 2, 3, 4. So if you have irregular time series, you have to just be careful not to to assume that the time periods between one and the other is the same when in doing your analysis, right? And there's a lot of statistics that allow you to work with that, yeah. But for us, the easier thing is just do equal time periods, right? It doesn't matter what they are. Does that answer your question? Yeah, okay. I mean, there was no reason why we particularly used quarters here, other than that companies typically report their earnings and things like that per quarter, right? I don't know if they do that in Vietnam, but in the United States, that's what they have the quarterly reported financials, right? Like when we went to Mergent online, oh, you didn't, but if you did go to Mergent, you would see that everything's reported by quarter. But of course, we could have done annual, we could have done yearly, could have done monthly, could have done daily, whatever, right? But quarterly is the common thing for that. Okay. So we interpreted the trend model. We just chose to use a linear trend as a way to describe the trend over the time period. And again, we just got to remember what the main thing that we care about was the slope, right? Because that told us the average increase or decrease over that entire time range, yeah? Which, for most purposes, that tells you the trend, right? Again, I don't necessarily need to be more detailed than that, unless your problem insists on looking at it in more detail, right? And of course, we're going to see this again a lot of time, but we understand what the slope and the intercept mean there. And then we talked about seasonal variability already. And again, it's good to I think the key thing about the seasonality is, you can let Excel or Megastat or even your AI calculate your seasonal indices and stuff like that. It's more important to understand how to interpret them. Like, what do they mean? How do I use them? And we got these seasonal indices here, and we talk about, again, it just says, what they mean, literally above and below. I mean, when it comes to statistics, the statistics just are what they are. What they mean in terms of your problem, that's where your judgment comes in, and whether they make sense. Like for Southwest Airlines, does it make sense that in quarter one they got 8.1% lower revenue than other quarters? Oh, this is a mistake. 1, 2, 3. That should be 4. Quarter 4, right? That I had quarter 2 6.2 higher, and again, for Southwest Airlines, we would expect a sort of seasonality, like seasonal travel patterns, high travel season, low travel season. And is low travel season predominantly in quarter 4, as this suggests, and high travel season is predominantly in quarter 1, as this suggests? That is either consistent with, in principle, what we expect, or it isn't, right? And if it isn't, we should investigate, right? Why isn't it, right? Yeah, why isn't it? In this case, I think it is consistent with it. I think, yeah, again, sometimes the quarters make it difficult because sometimes your seasonal patterns may overlap one quarter and another. And so you kind of have to adjust for that. Like, where does that go? So it looks like quarter 1 and quarter 2 are where our high travel season is, and it's lower kind of quarter 3, quarter 4. And again, for your particular one, does anybody have any questions about their seasonal patterns or non-seasonal patterns? Yeah.
Because Q4 is supposed to be year end, right?
Yeah.
So that's supposed to have a lot of holidays and Christmas, so the revenue should.
Yes, it should be, but it depends on where they're reporting it. So the revenue may be generated in quarter 4, but reported in quarter 1. I know. Again, it's yeah, you have to be careful about where they report it and where it's generated may not be the same. Okay, The key thing about the seasonality here is that when we talk about something like this 5%, which is you see in your report, you talk about 5%. What is that? Okay, the 5% is what we call a rule of thumb, you know? Rule of thumb is just something to help you aid your judgment. It is not like a mathematical or statistical law, right? It's not a definition either. It's not, we don't define seasonality as 5% of seasonal indices. We do not, right? It really depends on your situation, right? All we can tell you is that 5% is maybe something that would be notable, right? That in your revenue, if you saw a more than 5% increase, you would notice that. You know what I mean? It's like, it's not just in the noise, we call it. But in terms of like statistics, there's nothing that says that that is like a statistically significant value. You know what I mean? If you wanted to do that, you need to do a whole different kind of thing, right? Which we'll talk about in session 7, I think, or 8, session 8. If you, yeah, if you wanted to show that this is different, like this is significant, like I wanted to know that, is this significant seasonality? And whatever that word significant meant. And we'll talk about that today, exactly what that means. But if we wanted to say that it's significant in a statistical manner, you can't just say 5%. You know, that's arbitrary, right? What we're doing, we're just saying that 5% is something that you should take a look at, right? Because you probably noticed that, you know, but it depends on the company. I mean, if your company is like Google, you know, they have billions of dollars of revenue, right? And, you know, a 5% increase or decrease may not be noticeable, you know, given the variability in their revenue. You know, a 5% increase or decrease would be, you know, that would be normal for them, you know. Whereas in another company, maybe with smaller revenues, a 5% increase would be noticeable, right? It would be a big thing. So again, judgment, right? You guys feeling me here? All right. Yeah. Everybody makes this mistake at first. You know the difference between a mature and well-educated user of statistics and analytics when they don't resort to looking for set like formulas and laws. You know, you see a good person when they're using their judgment and they argue based on, they don't argue based on like, well, because it was over 5%, that's it. You know, no, they would say something like, well, you know, our revenue is like this. We see an over 5% increase, which, you know, that shows that that seems a little unusual for us because normally we'd expect something a lot lower than that. You know, that's the way they would talk, right? So you see a big difference. They don't resort to like rules and formulas and things like that. They talk about the situation and what the data really tells you relative to the situation, right? So that's where I'm trying to bring you guys, trying to bring you to that more mature version and user of statistics, not somebody who just quotes, you know, laws and facts and things like that. Okay, anyway, so don't do that. So it says rule of thumb, see 5%. Now, cyclical. So this is now brings us to where we were before. Irregular variation. Again, it's called irregular because it does not follow a set pattern like seasonality, like trend, right? So those are more, they follow a pattern, and irregular means we don't follow a pattern necessarily. It's quite important for us, and you'll see for our forecasting purposes, quite important to distinguish between an event which was something irregular but explainable versus something that was irregular, not explainable. And can you guys help share with me, why do you think that's so? Why do you think we want to distinguish between things, irregular patterns that we can explain that happened in the past, by the way? We're not talking about the future. We're only talking about in the past. We're describing our data. We see an irregular pattern. Some we can explain, some we cannot. Why is it important for us to distinguish those? What do you think? In terms of forecasting, let's put it that way. Remember, our goal is to forecast the next 4 quarters, right? Yeah. What? Okay, that's true. But what do you mean by that? What do you mean by more reliable? Yes, yeah, essentially that's right. By the way, I'm sorry, I'm very hard of hearing these days, so you have to forgive me if I do this, and you'll have to speak up. Yeah. It has something to do with, like, I don't know, getting older sucks, let me tell you. It's not because I'm going deaf, it has acid reflux. You heard that? And it's like gets in my ears and they get all stuffed up. And so I happen to love coffee, and especially Vietnamese coffee, which is very strong, but it gives me acid reflux. And so I end up not being able to hear very well. So I apologize. I'm not ignoring you. Yeah, just please just look at me and speak up. Thank you. What?
You can use the microphone.
You can use the microphone. Oh yeah. Well, too much trouble, right? Yeah. Just maybe speak up or come over. If you can use the microphone if you want. But yeah, essentially you're on that. The idea, it's like, I like that you mentioned reliability. So what do we mean by reliability? Well, we mean that, like, what we expect to happen in the future really should not change if we with the same information that we had, right? So it's reliable. It's like we give this thing, we say that A, B, and C, and then we get D, right? But if it's unreliable, if we have A, B, C, and maybe it's F instead, it could be D or F or so. So we don't want to do that. Like it would be unreliable if we talk about our trend and you said, like, well, in the future, maybe the trend will be positive or maybe it'll be negative, right? That's unreliable, right? You need to be either positive or negative, not possibly both, right? Unreliable. And the same thing here. If we have an event that changes, that affects our revenue, we need to be able to explain it. To explain it so that we understand how it affects. Why did it affect our revenue, and will it affect our revenue in the future? Is the important thing. An example for Southwest Airlines would be that here. Let's look at it. An example for Southwest Airlines is we see this irregular event. See, see, I was humming along all of a sudden I got a big jump. Yeah. Now, I don't know. I mean, again, we'd like to be able to explain this, right? Why did that happen? And if we can explain it, then we'd be able to determine whether we need to account for it in our forecast in the future, right? And so Southwest Airlines is a good example. Southwest Airlines, we saw this big jump here, and we split it up according to the jump. We split it up from here to here. Again, this is just to look at it, like what changed? How did it affect our revenue? I mean, so here, this is before that event, after that event, yes? And one of the things we see, of course, we saw the jump in the revenue. So see the big difference? So you can add a trend line here and add a trend line here, and we see that this trend line is way above that. That means that the intercept, right? See how the intercept, this is lower, that's higher, right? So that's one part of it. We also see that the slope changed a little bit. See the slope? 2988, 42 something. The slope decreased a bit, yeah? So this was going up steeper and that was going a little. So the rate of increase changed. In this case, we might call this a trend-changing event. A trend-changing event meaning that literally the trend changed. It didn't just go up, but the slope changed also. Now, it wasn't a whole heck of a lot, really, but maybe enough to make a difference. The key thing is like, what's going to happen here? Which trend am I going to be on this trend? Am I going to be on this trend? Or if I looked at the two together, kind of on the middle trend, right? Yeah. So if we can't explain what happened here, we don't know. It's unreliable, right? If I can't explain why did this happen, it would be unreliable for me to use it moving forward because I don't know, I don't know what's going on. So, if I told you that this was due to a merger, right? So Southwest Airlines acquired American Trans Air at this time period, right? It explains that what happened. Okay, they acquired American Transit Air. Of course, they're going to have a whole bunch more revenue. They acquired a whole nother airline, right? So their revenue is going to go way up because they've got a lot more business, yes, going on. So that explains that. The trend change also maybe just because the rate at which they acquire revenue is much larger, for a much larger company is also changed. Now, the thing that's important about this is that now that I've explained what this is, I know that this was due to that merger. I would expect in the future that merger still will have an effect, right? I'm still that larger company, yes? And so which trend is most representative of the future? Is it this one? Is it this one? Or would it be the overall one? Which is the orange one? Yeah, exactly right. See, now you see why you need to try to explain your events, right? Now, it's also possible I might have, so this would be a trend changing event. I could have a transient event also. Like COVID is generally a transient event. I mean, it happened, some stuff happened, like for an airlines, it was quite serious, right? Because they had travel restrictions and, people weren't able to fly much. And so their revenue, went down, right? And then gradually started to come back up again, right? Over a period of time. And eventually the restrictions were gone. COVID was kind of calmed down and it went back to normal. So we'd call that a transient event, right? Because it came and it went. It affected the revenue, right? It was irregular, but I can explain it. Now, the question is about what does that mean for the future? Well, I wouldn't want to necessarily, it wasn't a trend changing event in that it changed the trend in the moving forward because it eventually went away and went back to normal, right? Everything went back to normal. So, so I would just use the regular, I would maybe use the trend without COVID. You know what I mean? I'd take that COVID period out because it wasn't. You guys like my gecko shirt? Where's my gecko? Yeah. It's from Ginkgo. Yeah. You guys know? The good local brand, right? Yeah. So my wife insisted I get this. You're not leaving Vietnam without a good shirt. What? Yeah. It's kind of, yeah, with the gecko and everything. Yeah, cute. We have a lot of gecko in Hawaii. They're not blue, though. They're green usually. We call them Geico gecko. You can go look up Geico and has the gecko, Yeah. Anyway, so we see that the change, right? We see that in COVID, if we have that transient change, then we have to think about how do we account for that in the future. So we wouldn't necessarily change our trend, but maybe we would remove that COVID data because it might be outliers. They might be affecting our trend in a bad way, or maybe our seasonality, like seasonality during COVID for an airline. There was no seasonality. They weren't flying, right? There's not going to be a low travel season, right? So if you compute your seasonality, including that COVID period, it might distort the seasonal pattern, right? So we might just remove it and calculate our seasonality without that data. You see, never simple, right? Sorry, guys, never simple, but it requires thought, judgment, understanding, yeah. Well, fortunately, this was all historical, right? Fortunately. Yeah. And so you just look, you can say, well, here's, you know, what happened in those time periods. You can say, when did travel restrictions diminish? You know, when did I, and then you could look at the patterns. When did the pattern of seasonality return? When did I see my trend come back, you know, in the way it was? And so, you know, you can just use your judgment on assigning the period that you can explain why this is a period that's not representative. And that, by the way, that's common for outliers. When you have things like outliers, unusual, unexpected things, right? You know, you try to investigate it so you can explain it, and then you can decide whether you should remove that data or not. You would remove it if it's not representative, right? You just say, look, COVID data here from here to here just does not represent what we expect happening generally or moving forward, right? And so I'm going to take it out, for example. Now, many of you will see COVID data probably, and you have to think about how it affected your company. It will be an irregular event, probably a transient event. I'm trying to think for anybody. Bank of Hawaii is really weird, just to let you know. So Bank of Hawaii, you're going to have to be careful about COVID. COVID period it had an effect on their revenue, and it may be so pronounced that you should remove that data. Yeah. Other companies, you might actually just be able to, it had an effect, but maybe you would incorporate it as part of your company's business. Like I think maybe Google or something. I'm not sure. There's a lot more online shopping, for example. Yeah, but these are things you have to investigate, right? You wouldn't necessarily investigate it for FP1. For FP1, we just want to identify events, try to explain them. If we can't explain them, then we are forced, hear me, we are forced to consider them just unexplained random phenomenon, right? And that's going to make, that could cause complications for our forecasts, right? But because we're going to have to add more uncertainty into our, you know, thing. So this is the most difficult part of FP1, just to let you know, is identifying, explaining, and then getting the time periods right. Like you said, it's kind of, you know, where does it begin, where does it end? Is if it did, some things don't end and some things do, and explain. So here's where Google and AI are going to be very helpful for you. So one of the things you could do is if you see a jump or a trend change. I mean, another thing to look for is not just a jump, but you can look to see like Netflix. You'll see trend changes. You'll see that it kind of was going along like this. Just try to imagine linear trends. Like it was kind of trending like that. Then all of a sudden you see it go up like this, right? But maybe it was going like that and then another trend like that, you know? So what's the difference between a trend like that and something like that versus a curve, right? So we can describe a trend change, and there may be something that happened with Netflix. Like Netflix, they increased their subscription prices. Well, that was probably not the wisest thing for them to do, right? Yeah, yeah, right. Right. It changed their subscriber base a lot, that's where they make their money, right? But plus they also stopped password sharing, right? Yeah, and that may have affected things too. So you got to look for things like that, and you got to understand like that was. I think the subscription increase, you know, was probably a trend changing event, right? Because you know they're not decreasing their prices after that. Yeah. So it can be tough. So here's where it could be your friend: is you look for these anomalies, we call them. That's kind of an anomaly, right? And there's several tools that we look for here. That we can use. Let's see if this is pretty good. And please, again, don't look for like clear answers and stuff like that. But here, here's the, so for most of you, you'll have under the like irregular tab or something like that. What we'll do is we might have the deseasonalized revenue. And the reason why we look at the deseasonalized revenues, we don't want to get confused by the seasonal pattern. Like Costco has really strong seasonal patterns, and it might make it difficult for you to see some of these irregular things that are not seasonal because they kind of get masked by the, right? So we look at the deseasonalized as a way to kind of get rid of that variability so we can see the irregular variability. Netflix, you don't have to do that, right? Won't make a difference, right? And then we also might look at the detrended. The detrended means I just see how I have kind of a trend going up. So you just take that linear trend and just remove it. So that instead of seeing, it might be hard for you to see irregular jumps or something like that when it's always going up or always going down, right? So we just get rid of that, and then you can start to see, here we see kind of normal, unexplained variability, right? Kind of sometimes up, it just wiggles around, right? But every so often we get up, right? Oh, that might be irregular. See how that little book there corresponds to that little jump there? Again, would have been harder to see maybe without that. And then, oh, wow, like here we obviously saw, right? Yeah, but you can see. So again, it's just a tool. It's a visual tool to help you identify areas that might be. And sometimes we look at the cumulative also, and that might help us with trend changes. Yeah, trend changing events. Okay, anybody know what this was? This is Southwest Airlines again. Yeah, this is 2019, end of 2019 to 2021, 2020. Yeah, it was COVID. Yeah. Remember how I said everything was fine? No one's flying, right? Every travel restrictions. Finally, it went back to normal again. Transient event right here, COVID. So typically the way that you're going to want to investigate your events is when you think you see an event, you'll cut it before and cut it after, right? And then look at your, right? That's why we have it. Let me see if I have another one here. Yeah, so the way to cut it into two series is very easy, okay? In Excel, all you do is you take your revenue and you think you have an event and you just split it up before the event, after the event. And if you have multiple events, you can make more columns, right? And then you just take this whole thing, plot it, right? And then you can add trend lines and you can see, right? Yeah, and again, the R squared here, the R squared doesn't tell you how accurate anything is. It just tells you how well the trend explains the variability in that time period. So I wouldn't make too much of the R squareds here, but more importantly, looking at the trend changes, right? Whether the slopes, see how the slopes are different? And of course, the intercepts are different, right? And then the more important thing is to say in that time period, that's when the merger happened. We expected this exact thing, right? And now we've described what the effect of the merger was. Yeah. So same thing for anything you do. That's what your aim is. Let's try to work on that now for the next 15, 20, 30 minutes. Does that sound good? In your groups. And I will come around and I will try to help you. I don't always have all the answers to this because this is real data, right? And it's really up to you guys to investigate. You don't have to get everything perfect right now, but let's just try to identify some things that we need to investigate. Okay, so go ahead, let's get to work. You guys can move the desks around if you need to. Who wants me to come over and help them right now? Anybody? Netflix? Okay. Let's take a look at Netflix. Well, okay, again, here we're looking at trends. Can you move that out of the way? Yeah. So you see, I was kind of going along at a trend there, then there, then there. See how it's different? 1, 2, 3.
Okay,
So I would split it up along those and then investigate what happened in those time periods. You could do a Google search, like in Netflix, why would the revenue rate decrease, you might say, or ask ChatGPT or something in that time period, around that time period, and then see if it comes up with anything reasonable. And make sure you check the source. It has to have a source because it makes stuff up. You don't want to make stuff up. Okay, so yeah, I think you didn't you do that here? 1, 2, 3. Looks like you did. Yeah. So now just investigate, like, what happened in this period. 2021, 2020 quarter. I say you can ask your Gemini or ChatGPT or whatever, or just Google. Just go to Google and just what happened in around Q4 2022 that might affect the Netflix revenue. And
we only can maybe gather some information that we know from the public, but actually if it's something coming from inside of business, we don't know.
Well, these are all public companies. They have to disclose it. Yeah, so don't worry. It's there. Yeah. If they change their business model, they have to say so. Yeah, like they have to because people are buying their shares, right? So they have to explain to the shareholders, what they're doing. That's the law. They can't do secret things. Yeah. Trust me, you'll find it. You'll find it. Yeah, you guys. No. So what are you guys thinking here? Okay, Bank of Hawaii. Oh my God, Bank of Hawaii was like riddled with events. I mean, you can see, right? I mean, what happened here? So they were going like here, then here, yeah, here, and then here, and then there. Right. Yeah, so something happened here. Yeah, COVID, right? And then something happened here, right? And then something happened here. So try to find it. Yeah, I would split it up. 1, 2, 3, 4 parts. And then try to say, then maybe do a Google for Bank of Hawaii, what happened around it? Yeah. Did you find things? Other than COVID? Yeah. They're there. You may have to dig, but there's stuff. Yeah. What? Yeah, interest rate. There was a big change in interest rates. I think over here, right? Yeah. So they had a lot of rate hikes. Yeah. Whereas over here, yeah. Yeah. So again, just try to explain. You may have to do more investigation later, but for right now, just identify areas of anomalies and then start to investigate. Yeah. And then, because later on, we may have to deal with this. Yeah. Right.
So because this industry is new for all of us.
Yes.
When we see the banking industry, we assume that they will have the seasonality in the.
Okay, so that's tough. Why do you think banking has seasonality?
So that's how can we validate for our time?
Well, again, AI is going to make something up. If you tell it, explain to me why Bank of Hawaii has seasonality, it will make something up. If you tell it to explain why it doesn't have seasonality, it'll also make something up and tell you why it doesn't. So you guys have to decide your judgment, what you think. Now, you could go look at some of the reports from Bank of Hawaii, but I'll tell you, banking tends not to have much seasonality. I mean, think about it. Their main business is what? Loans, right? Yeah, like home loans, business loans, things like that. There's not really a whole lot of seasonality. Maybe for home loans there might be, but maybe not. And plus they also, what other business? There's fees, the banking fees and things like that. And again, probably not a whole lot of seasonality there. So are you seeing seasonality? Like, do you see like indices? No. So don't try to make, so if your theory is that we probably don't expect a lot of seasonality, if any, because of the nature of the business, then you just go look at the data and say, look, we don't really see a lot of seasonality. Okay, we're done. That's it. Don't try to explain something that you don't, you don't want to contradict yourself, right? Yeah, okay.
Another question. So because as you mentioned in the revenue of Bank of Hawaii, we have many like type of products. So is it still possible that there is a seasonality for each type of product?
It's possible, but we're talking about overall revenue seasonality, So maybe there are some seasonal products, patterns like, I don't know, like maybe one I think that personal loans might go up during the holiday season so people can buy toys for their kids. I don't know. But I mean, again, we're talking about the seasonality for the all the revenue streams, not just particular ones, right? Yeah, this is the revenue for the whole bank. Yeah. Okay, guys, how's it going? Yeah. Costco. Okay, so we see a little blip here. Yeah. And so before and after, it doesn't look like much. Yeah.
The slope is very.
I see that. Yeah, the trend looks similar, but maybe a little different.
Yeah, a little bit.
Yeah. Do you know what that was?
We are looking for some of the.
What happened around this time period?
Okay, so I'm looking at comparing the stock to this, which you probably don't like, but ChatGPT.
Yeah.
I looked it up. This
Yeah.
made a little plot.
Yes.
Here.
Yes.
It's the big increase in revenue.
Yes. Right. Stock price.
I compared that to, and I put that into ChatGPT.
Yeah.
Why do revenue and stock price increase so quickly? Q4 2023 is because the AI boom and people were, at least the stock price is because people were expecting AI to start booming.
Yeah, but again, the stock price and the revenue are not necessarily related.
Okay, true.
You know what I mean? It's kind of a sketchy relationship.
This
Yeah.
just popped up, so
Let's just say it's complicated. I wouldn't use the stock price as a way to describe this. I mean, again, that little blip, I think it's more of a curiosity than anything, because obviously it didn't really affect the trend that much. It just at short time. So there'll be a transient event is probably what you're looking for. Right. So yeah, what was it?
Okay, I'm looking for many information.
Yeah, and if you can't find
including
it,
the member and also the company events, and we see that no major company events, but in terms of
there could be
reporting,
economic events.
like,
Yeah.
in terms of reporting of the fiscal year, it's very different because Costco fiscal year is added.
Yes. Right.
August is not like December.
Right.
31st.
But they didn't change it.
But in that period, because they are 33 weeks. It's not 32. So it's just count more weeks, one more weeks.
Would that explain this?
Yeah.
Just one, only in that one time period.
Yeah.
But what about how about the other time periods? They still reported the same way, the other ones, didn't they?
Yeah.
I don't think so. I'm sorry. Yeah, I don't think so. Good try. Yeah, I don't buy it. Yeah.
Maybe inflation, because of inflation was hitting a point. We all expected so revenue looks higher.
Yeah.
Because inflation was hitting a point where more money is coming in, but it was worth less.
Yeah, let me see your graph again.
I also looked at the
You got
macro indicator.
Okay, so I'm seeing this. I'm seeing here a trend like that, and then I'm seeing a trend like that, and then I'm seeing a trend like that, and an anomaly. So I'm actually seeing three things. One here, two here, and three there.
Okay.
Yeah. So I think you should look for something here and look for something there. Here,
Yeah.
and yeah, and then you you can look for this. It could be like this and like this. It could have been 1, 2, 3, 4, maybe.
What quarter?
There was definitely that looks like a transient thing. Now it could be. I'm not sure if it's the reporting, but there's something weird about Costco in that their seasonality also increases, right? Mm. And this could simply be an anomaly based on the way that you deseasonalize, it's just sort of more pronounced there. So I would suggest splitting things up here, 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 and then, well, I don't know. You can decide. You can decide to do all of that or bit and bit. Okay. So do that, and then see if you can explain it. Yeah, or at least explain the last one as much. Again, if you can't explain that, then we'll just say, yeah.
Yes, unrelated.
Mm-hmm.
At 3:30, I
Yes.
have a pretty amazing event happening.
Oh,
I
okay.
assume that our class is going to start at 8 a.m. and end at 3.
Oh, you did it?
because, Yes, I have a burger festival hosted by home.
Well, you got to go.
I know. So at 4:15, I need to be in place,
Ah.
which means I need to leave here maybe 3:30.
Yeah,
And I'll be wearing this, so I can do some
just go. Yeah, go.
Yeah.
I mean, we'll catch you up tomorrow.
Yeah, and I'm gonna miss the dinner too. You guys are having dinner, but I can't.
Doing burgers.
I know. I'm plenty of dinner. I'm gonna be eating every burger.
Wow,
Making the.
that looks so cool though. I'm really excited. That's funny. Yeah, bad timing, but
It's. I know.
Yeah, but you got to do what you got to do.
I was gonna go to Hanoi,
Yeah.
but then I saw 3:30. Classes at 3. Cool, I can make both.
Where did you see that?
I just that was a full assumption because we do
Yeah,
online. and
right.
offline.
No. She told me 9 to 4.
Yeah, I know.
I would have
It's
been
my
happy
fault.
to do 8 to 3. That would have been fine too. Don't worry about it. You're not going to miss much.
Okay.
Yeah.
But
We'll
it's
catch you
actually
up.
group-
Yeah. We'll figure it out. Yeah.
Sorry about
Thanks for letting me know. That looks like a cool thing though. So
Yeah.
yeah. I'm highly supportive of a burger festival. Okay. Right back, you guys. Good that you took a break. I was about to suggest that. Make sure you guys take a break also. Yes.
Like American hospitals, like, right, the only bridge that comes. And that's what we're talking about. And then they have these.
Yeah, because how about it? So ignore. Yeah.
Oh, that's. Yes, so that could fit in AI. Because now they're looking at building products. They all want now hospitals. Because they. Or you need a big. All of That's good. How much of your revenue comes from this division?
Yeah, no, I knew that never. Yeah. Oh,
Merchandise, and they also sell gas.
Yeah.
How much is gas?
Very illegal. It was very illegal.
Now, membership fee is only 2%. And then the rest is covered. So gasoline is 12%. So if inflation goes up, inflation rises, then revenue gasoline. Basically, the number of inflation goes up. So, they need to
But it used to be on the previous.
yes, but also it's for savings. Right? So you buy.
Okay, guys, say we got to why. He needs to be out of the waste. Everybody said here's why. But I think if I see what I'm talking about, I will spend next. I will buy gas station next. I will go. So okay, what is our
This might be inside the back.
okay.
But then just, I think we know. Yeah, I was like, this is the right there.
Yeah.
Yeah.
This is that. The creek all.
Yeah. Yeah, and then it goes over.
I have to do the same pattern. Very easy to know. But very cheap jump, very pretty well.
Yeah, we already mentioned that.
Yes, that's right.
No bar, it's a different from off. But there will be the type of managed revenue increase significantly or that. So we have to replace. Yeah. 1 week actually.
Let's try to get started. And again, yeah, bring your goodies inside.
Wow.
Good.
About the weather is here. compared
It's
to
fine. It's a little hotter and more humid. Yeah. So I've been here many times. Yeah.
Years, several years ago, you also.
Yes. Yeah. Yeah. I've been coming most years for the last maybe 8, 9 years, I think. So, yeah. So, yeah, frequent. But of course, everything changes very fast here. Oh God, yeah. Every year I come here, so much new stuff. Yeah, especially Hanoi. Oh my God, it used to be like, it's different now. Now it's like a big city, big new buildings, crazy.
What do you feel about your vision for the future?
Of Vietnam?
No,
Oh.
US, because US is a big country, which is Africa's even the global economy. So what do you feel?
What do I feel about that? It's a little concerning now, I think.
Because as Vietnam, there's more countries.
Yeah.
So actually, we also care about what will be, what will happen in the future.
Yes.
That might affect the economy.
Yeah. Well, I don't know. I think that many of us are not a little nervous about our president is not very wise. Let's just leave it like that. He's more interested in talking about himself and being, and not really caring so much about the people and the economy.
This is not one change in the really depend on the parties.
It's true, but there's the people around him are the ones that I'm nervous about. He doesn't, but they use him as a way to say, we're going to do this, we're going to do that. And we don't like it. Yeah. Yeah.
Best, but each stage also have a different kind of
Yes.
law.
Yes. Yes.
Work on their own.
They can, but it heavily influenced, Yeah, a lot of anyways, we have a lot of problems with that right now. But in terms of economy, we don't. I think like this idea of like setting tariffs and all that is very bad. Yeah, it's really bad. Yeah, it's not. I don't think it's helping anybody, and making trade difficult. And seems like we're doing is giving away business to other countries.
Needed.
Yeah.
The way the government trying to take something to require the other countries to govern those countries on the table.
Yes. Right.
But the reason that they gave over to the other countries was just like bullshit.
Yeah, exactly. Wrong reason, right? They want. Yeah. Yes. Anyway, so maybe in 3 more years, I'll be more encouraged. But right now, not so excited. Yeah, not so excited. Have a break, and then we need to start again.
Yeah. That's the reason I mean,
Okay, we're gonna get started again. So get a break, get a tea or whatever you need, and we must move on.
Okay, sorry.
Oh yeah, come. What's up?
Yeah, our team just broke down the trend line into four sub trend. Right?
Yeah.
And this means that in this period and the period, the later one is increased very much in terms of revenue.
This one?
Yeah.
Yes.
Which is steeper, right?
Yes, it's steeper. So the rate of increase was higher.
And then it means that after that
It stopped.
Happened.
Yeah. Yeah. And then here something happened, maybe bring it back.
Yeah.
Well, I don't know what this was.
Wow. Understand. Okay.
Yeah.
What we try to look at this and explain.
Yes, you need to try to explain. Now, again, some you may not be able to explain. If you can't, then you just combine.
Yeah. Understand, sir. Thank you.
Huh?
How about the tea break?
Oh yeah, I had. It was very tasty. Oh, okay. Oh, I like the little green jelly one. That was very good. Yeah. Oh, very tasty. Let me get everybody back in though. Yeah. Okay, you guys, let's go. We got to get started. Bring your stuff and come on back in. Time to do some forecasting. A BBF. What? Oh, very much. I love it. Yes, very much. Weather's not too bad. Yeah. Best time, right? Not too hot. Oh, really? Oh, interesting. Yeah. Well, lucky me then. Yeah. 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 Oh, good. Yeah. I see. Yeah, Hanoi was surprisingly warm. Yeah, not hot, but usually it's kind of cold with coldness on. Yeah, it's very good. I'm enjoying myself very much, but I hope that you also appreciating.
Because your way of thinking is, like you said, it's really different. You know, the usual statistic class I studied.
Yeah.
Usually they just say, "Oh, this is the set." So
Yeah.
you report it.
Yeah, do this, do that. Great.
So it's really because I'm not really versed in numbers.
Yes.
Statistics.
Yes.
So at first I really there's the two way of different the way I learn,
Yeah.
the way you talk. It's like opposite. So I was super confused in the start of class. But
Now you're getting it. Perfect. Excellent.
So
I'm
it
very
was-
happy to
it
hear
was
that.
fun.
Oh, good. Thank you. Well, keep enjoying. It always goes better when it's fun. Yeah? Okay. All right, you guys. I know that you're enjoying working on FP1, irregular components, but sadly, we must move on because we have so many other things to do. I promise you the other things coming will also be fun, right? I didn't say easy, right? But fun. It should be interesting, right? You're finding this interesting, right? Yeah. Are you starting to see how you can use your statistics as a way to understand, right? Tell stories, see what's going on, get insight, right? That is the main thing. It's not about, there's no magic, right? No magic. It's just tools, just ways to help you look at things and gain insight. So speaking of that, it's now time to talk about forecasting. Our ultimate goal for our forecasting project is, of course, to do a forecast of our company's revenue for the next 4 quarters. Now, we're not actually prepared to really do this, and we need to understand why. At this point, what we have is we've described our time series. Now, of course, there's still more you need to do. Obviously, you'll go back and look more carefully at your events and describe things more perfectly if you can. But let's try to actually take the various descriptions of the components and put them together into a forecast. Now, to do this, we need to understand what a forecast actually is, right? And what will be useful. So again, I think you already know, is predicting the future value of a time series. That literally the word forecast means that. We're thinking about just the future values, meaning that I have a sequence of values from 1 to 10. I'm going to look at 11, 12, 13, right? Predict 11, 12, and 13. Technically, when we're talking about forecasting in this way with a time series, it's extrapolation. Because extrapolation means you're looking at values outside the range of data that you have, right? And right now we have this time series of data 1 through 20 something or whatever it is, quarters of revenue data, and we're trying to predict values outside of that time range, yes? And if I'm predicting inside the time range, that would be interpolation, yeah? And it's different. And the difference between extrapolation and interpolation is that if I'm predicting something inside the time range, I already know what values are in that time range, right? So it's almost nothing to predict, right? I mean, think about that. All I'm doing is I'm interpolating, meaning I'm kind of like maybe looking between like time periods, like maybe instead of exactly what was the revenue at quarter 1, 2020, I might look at like what was the revenue in January in 2020, you know, and so I might be interpolating. I have my time series going by quarters. I might try to interpolate the values by month. Does that make sense? But you see, that's different. That's not really predicting anything. Yeah, I'm just kind of, I already know what the values are. I'm just trying to think about like more detailed what the values would be in between there, interpret between it. So extrapolating means extra going outside, right, of that. Typically when we extrapolate things, you have to be quite careful because you do not have data to support what you are predicting, right? That's directly telling you what it is. So anytime we do like a prediction, you always have to have a model, right? Based on assumptions, a model that will allow you to do that prediction, to do that. It can do for interpolation too, but but a model for doing the extrapolation from that model. And of course, it's going to be based on assumptions. At this point, the assumption, we have to think about the components and that we made for our time series. We have the trend component, the seasonal component, and then we have the irregular stuff, right? Yeah. So what are the assumptions that we need to make for those in order to be able to predict something outside of the time range is the question that we will discuss here. We're going to look at the key thing is that the model variability time series, we modeled the variability, model meaning that we made models of the variability of those time components, assuming the historical data is representative of the future. That's our main assumption, that the historical data is representative of the future. Now, that it shows up differently depending on the component that we use, right? And it says this is some serious assuming. So let's see what this, by the way, you know the word assuming makes an ass out of you and me and Ming. You know, ass like akole. And Hawaii, akole. Yeah. I don't know what it is in Vietnamese. What is it? What is Pom? Pom? Okay. And you know you sit, right? Okay, so anyways, let's think about the assumption. I don't know what I have here. I don't know. Let's see. I don't want to do through all this stuff. Let's think about the assumption of the trend component. What assumption must we make to make predictions or extrapolate for the trend component? Okay, linear. That's not so bad, actually. But what would be another one? Remember that it says the historical data is representative of the future. In other words, we're thinking that the trend that talks about the variability over a time range. Yes? So in the future, we're going to have to say that variability that's explained by the linear trend extends to the future. In other words, not just in this time range, but that trend will be the same in the future. Now, I think you just went and looked at the irregular component, and many of you found that trend changes. Yes? And it changes at any time, unpredictably. Yes? So think about this assumption you're making, that if we are going to use the trend component for predicting value in the future, we have to assume that trend in the historical time period will be exactly the same in the future. Now, do we have any way of knowing that's true? Do we have any way of validating that is a reasonable assumption? No. In fact, most of us would be pretty damn nervous about making that assumption because we know that at any time that trend could change, right? So think about that. This is an assumption that we will be making that is extremely strong and not well justified. Yes? Most of you would not be confident in making that assumption, would you? Would you be highly confident in making the assumption that the trend, even for your company now, no matter how good it looked historically, right? Would you really want to stand up there and say, yes, that's exactly the way it's going to be in the next 4 quarters? You might say, well, it might be close, but I don't know. You know, something could happen and, right? Yeah? So this is something we need to keep in mind. That assumption about the trend is extremely, we call specious, dubious, questionable, not necessarily good, right? Now the point is not that we shouldn't make that assumption. We're going to have to make that assumption if we're going to use that linear trend for extrapolating in the future, right? We're going to have to say the trend is representative. It's going to stay the same for the next 4 quarters. We're going to have to do that. The question is not should I make that or should I not make that assumption? It's is it useful for us to do that? Like if we make that assumption, is it going to be useful? Are we going to get anything useful out of this? And that depends on what you're using your forecast for, whether it's useful. If I'm trying to like predict like exactly how my revenue, like what my value of my revenue will be for the next 4 quarters, and I want to predict that with certain confidence and reliability, not so useful, right? Because I can't get any reliable confidence in the accuracy of that forecast, because that trend component, I have no idea if that trend component really will be the same, right? The data in the past will not tell me whether in the future it's likely to be like that. It has nothing to do with it, right? You know how they say past performance doesn't dictate future performance, right? This is it, right? This is it. So if I'm trying to like have a prediction with accuracy and confidence that's reliable, and I can take that, I can bet on it, yeah? This is not gonna work. That assumption is not good. But if all I'm trying to do is like maybe get an idea of what I would expect, like here's what we would expect our revenue to be, then maybe it's not so bad, right? Because I'm not trying to say it's gonna be precisely this. I'm just saying, well, we kind of generally expect that if all things stay the same, then this is what we'd expect. Now that may be useful. That may be useful for setting expectations, right? They do that, right? In the companies, they often will have set expectations for earnings in the future, and they might give a forecast or something like that. Okay, but they always qualify it. They always say, oh, but, this is only setting expectations. We can't guarantee this. We have no confidence in this. We don't have any confidence that this is what's going to happen because of this assumption that the trend is going to maintain the same. We don't know, right? There's no way for us to like get anything on them. Okay, so that's number. What about the time series? What about the seasonality component? The seasonal component? What assumption do we need to make there? That if our company has seasonality, right? Costco, yes. Netflix, no, right? If my company has seasonality, that the seasonal pattern that I've seen historically will remain the same for the next 4 quarters. Now is that a bad assumption to make? No, not really, because you would have to have really serious structural changes in Costco to have that seasonal pattern change, right? And I don't know what would happen for Netflix. I mean, you think Netflix is suddenly going to have seasonality in the next 4 quarters? No. And even if they did, it probably won't show up for a long period of time. So, right? It doesn't matter. So the seasonal assumption, the assumption we make for the seasonal model, because in principle, we have a way to determine whether we have seasonality or not. And we're only describing what that seasonality is in principle. And if we see what we expected in principle, then we would expect in principle it would be the same in the next 4 quarters, right? Therefore, that assumption is maybe more reasonable, right? Yeah, so we got one unreasonable one, one reasonable one. And now for the irregular component, that becomes a little more tricky, right? Okay, this is why we spent some time here investigating when we saw irregular variation, can we explain it, right? If we can explain it, then we can determine whether in principle that irregular component applies to the future. So for example, in Southwest Airlines, after the merger, we would see that in principle that after the merger, the trend that changed would apply to the future, yes? And hence, when I'm doing my forecasting, I'm gonna use that trend. I'm gonna use, remember the orange one? You all said orange, right? I'm gonna use that trend because in principle, that's the one that's representative of the future, right? Now again, it's an assumption I'm making, right? Because something could change, right? But at least in terms of as far as much as I know, that's the one that's most representative. Yeah, I wouldn't want to use the other trend or maybe the average trend from all of the over the whole period, because I know I could explain that this is why the trend of the revenue changed, and I don't expect it to stop, right? Yeah. And so you need to do the same thing. So in your irregular components, you're going to need to think about what trend is going to be most representative of the future based on your understanding of what that trend represents, what period of time that represented. So some of you have if it's a transient event, then you would be like, well, the trend didn't change, it just caused some problems. So, your decision would be, do I need to account for that irregular data or not? Like in Bank of Hawaii, maybe the COVID part, you'd say, no, I don't need to account for that because that's just messing up things, and it's not relevant for the future, right? But if I did have a trend change, like I think Google has a trend change, right? Yeah, you're going to have to say, okay, I know why this is a trend change, and I think this trend is going to be the one that's in principle representative of the future. And then Netflix, the same thing for you guys. You guys got to decide which, is that understood? So, and again, these are assumptions that we're making. Now, these assumptions on the irregular components, it depends on how confident you are in your explanation on how good the assumption is, right? You know what I mean? It's like so this is why if you can't explain it, we have to just treat it as chance variation. Does that make sense? Yeah. If we can't explain it, it means we can't make that assumption that is representative or not. Yeah. Okay. All right. So how do we do the forecasts? They're really quite simple. The qualities of a forecast, I mean, there's a whole bunch of steps to doing it, but forget it. There's lots of different forecasting methods. We're going to start FP1 with a naive forecast. A naive forecast is simply going to be that we're going to make the assumption that the past what is it doing? Trying to see all these different ones. Multivariate. Well, as I said, there's lots of different forecasting things. They all depend on making a model for things. And for time series, all the forecasting approaches always take the components of the time series and put them together based on certain assumptions, right? As the way to do it. So you'll see there's a lot of things like ARMA and GARCH and all these things. We're not going to talk about these. They're more advanced. You want to use them, you can ask your AI to help you with those things. But in this class, we're going to use naive linear trend. And we'll want to understand why it's called naive, or in the Japan, they say naivu, right? Naivu, right? And then and multivariate co-integration. This is what we're going to do in FP3, which is going to provide hopefully some more meaningful and non-naive forecasts. So we're going to work our way up to that. So the time series models that we're going to use for naive, there's two basic ones. We have an additive or a multiplicative model. And simply, an additive model is I take the series components and I add them together. Take the trend plus the seasonal plus the cyclical plus the irregular stuff, right? Or random, we might call it random component. The multiplicative model, you multiply them together. You can also take combinations like part multiplicative, part additive, stuff like that. These are just basic things. These are basic models, right? Like ARCH and GARCH, they do more complicated versions of these kinds of things. For us, what we're going to do is we're going to take the trend as represented by the linear equation here, this intercept plus the slope times the time period, right? Yeah. and then we're going to multiply that by the seasonal index if we're for time t, if we're predicting that. And then we might have, if we wanted to have the irregular component, we would multiply that in there. The way that we're going to do it for FP1 is we're not going to look at the irregular component. We're just going to choose the data that we're going to use, and that will split this up. Okay, anyways, this is a lot easier done than said. Naive forecast is simple. The pattern that we observed nearby will continue into the future, right? Again, we talked about, like, for the seasonal component, that seems okay. For the irregular component, it depends on how well you were able to explain it, right? And for the trend, the linear trend, we just have to throw up our hands and just say, well, this is what we would expect if nothing changes, right? Yeah, again, not a great assumption to make, yes. So as a result of making those assumptions, we can't really get any high reliability. We can't get any meaningful confidence in the predictions, okay? That's because we can't, there's no way to define what we mean by confidence and reliability under the assumption that we're making, like, it's just going to continue the way it is, right? Because we have no data to allow us to measure or quantify, that. It's just, it's a completely unknown territory. Yeah, does that make sense? Yeah. So when we talk about, like, confidence and reliability, we have to have something to base that on. We don't have anything to base that on for here. So this is a big mistake that my lovely Hawaii students always make. They always look at the R squared of the trend line and say that, oh, the R squared is really high, therefore we're getting accurate and reliable predictions. And I'm always looking at them and going, you haven't been paying attention to class, right? No, you're not. You are not getting accurate and reliable predictions. The R squared is just telling you how well the historical data fit the linear trend and nothing more. It doesn't say anything about how it's going to fit in the future because you don't have that data, right? And in fact, if anything, you probably would think it's not going to fit that very well. So I don't know. So yeah, you guys get it. We're not going to make that mistake, right? Not going to. So don't talk about the R squared in your previous stats class. They may have burned that into your brain. R squared tells you how accurate and predict, blah, blah. Baloney, right? R squared is just another statistic. It only tells you and is meaningful as relative to the particular thing it's trying to describe, right? In this case. So naive forecast, is pretty stupid simple. Look, if I'm selling, stone wheels, and I've been selling, and our sales have been increasing at 10 wheels per week. We sold 250 last week. Next week, how many are we going to expect to sell? Yeah, exactly. Right? Yeah. Now again, is that not useful? Not really. It can be useful because it tells you what to expect, right? Yeah. Do I actually have any confidence that I'm going to sell 260? No, not at all. It's just kind of an aspiration, right? It's kind of like, well, if all things stay the same and we keep doing as well as we're doing, you may not want to. Maybe you would want to actually make it 20 wheels a week, instead of like that. But in any case, that's it. If you have a high degree of regularity or you have seasonality in your future forecasts, you will need to account for that. Think about it, right? So if I am going to be making a prediction for quarter 1, 2, 3, and 4 in the coming year, and I have seasonality in quarter 1, 2, 3, 4, just looking at the linear trend and extending that to quarter 1, 2, 3, 4 will only tell you the average increase per quarter, right? It will not tell you about how much more above or below, right, for each quarter. Yeah, that the linear trend isn't going to do that for us. It doesn't capture that information, does it? right? It doesn't model that. It models only the trend. It doesn't model that seasonality. So if I have that seasonality and I know I expect to have that seasonality, I need to put it back, right? Which is why we model the seasonal component. We model the seasonal component to figure out that in quarter 1, 2, 3, 4, how much more above or below would I expect? And so simply, I'll use the linear trend to get what the average was, and then I will add the seasonality for each quarter as I would expect it from the seasonal component. Easy peasy, right? Yeah. It's as simple as multiplying the seasonal index. You know, it really isn't hard, I promise you. Okay, so let's go do this. So the naive forecast, again, it's not hard to do, is you figure out which trend you believe based on your explanation of the irregular parts most represents the next 4 quarters. Which trend do you think represents the next 4 quarters based on your understanding of why that trend occurred historically? That makes sense? Usually it's going to be the last trend. Like if you had an event, right, it's usually going to be the last trend. An exception might be for COVID. Like if there was a big COVID event and it screwed things up like in Banco, you know, it may not be the last trend. It may be the trend before that. Because after COVID, you might not have enough data to really establish a good, stable trend, right? You might remove the COVID data and look at the trend before and after, right? And or something like that. You know what I mean? So this is judgment call. Again, what is going to be the best representation based on what you can explain? If you can't explain it, you got to use the data as it is. And then what we do is we just take that trend and then we extend it 4 quarters, right? Get those values there. If I have seasonality, I get the seasonality for those quarters, the seasonal indices, and I just multiply them. So I would get the deseasonalized prediction first, and then I reseasonalize it with the indices and put it in there. And that's it. And then you can go graph it and see if it looks, you know, looks reasonable. It probably will, right? Again, not a whole hell of a lot of confidence in this, right? But it certainly would tell us what we'd expect, right, to have. Any questions so far? Yes.
So can we apply the transfer into the business plan?
Into a business plan? I don't see why not. Why wouldn't you be able to? I mean, again, we're only looking at historical data and we're trying to describe that and then make a model for it. So once you've made the model for it, you can use it for whatever you want. Just make sure you know the assumptions you're making and whether they are reasonable for the problem that you are, you know what I mean? If it's not reasonable for the problem you are trying to address, right? Or it's not useful, then no, you can't use it, right? But if it is reasonable, if the assumptions are reasonable for the problem that you're trying to address, and it's useful, then yes, you can do it. That's just the way it always works. Yes. Yes. Yeah. There's nothing else you can do when you think about it. What else are you going to do? This is the data that you have. You only have historical data, and we don't have like future data. You know, like what are we? Unless some of you are psychic, yeah. I'm thinking. I'm feeling an increase. Yeah. Yeah. Yes. Yeah. Yes. Yeah. Well, I'll tell you that the most common kinds of forecasting in business are not naive forecasts. They do a little more. They do the kinds of things that we're going to do in FP3, what we call co-integrated forecasts. So they look at factors. What kinds of things that we believe affect our company? Maybe historically, we understand that they've affected our company in this way, or we understand that it will affect our company in this way, and then they make a model using those factors. And then what they do is they predict what happens with those factors, and then they use that to predict your company's business. The reason why they do that is because you can actually get confidence and reliability from that, and you can also explain it. Let me tell you this, by looking at the linear trend, right, and just expanding it for the next 4 quarters, it does not explain anything. It doesn't say why our revenue is going to be increasing or decreasing. It just says that it had been, therefore we think it will continue, which is not an explanation, right? But if I told you that we think that interest rates are going to increase next year, right? Or gas prices will increase or something like that. And we know how interest rates and gas prices affect our company, right? In this way, historically. Then we could say that, okay, if gas prices increase and interest rates increase, this is how we would project it affecting our revenue. Yeah, that's the way they do it, because now it explains it. And then you can strategize too, right? You can say like, okay, if we think the gas prices are going to increase, what can we do to manage the negative effect that we expect to have? Yeah. Mm-hmm, mm-hmm. Yep. Yep. Yeah. 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 One, it's controllable, and two, it's more less variable, right? Yeah. Yeah, it's less variable. It's under your control, more under your control, and it's more predictable. Yeah, exactly right. So that's exactly what you do. You take the more controllable and or predictable factors and then use those factors to do it. That's exactly what we're going to do for FP3. But right now, FP1. Okay. Okay, so let's go ahead and try to do the forecast. Again, this is not hard to do. I want to hide these components. Let's see, hide that. Okay, so let's go to here. Let's say here, maybe I'll go here. Let's just say I wanted to do the forecasting for Southwest Airlines. Okay. Okay, so watch this, because this is what you guys are going to do soon, is that you're going to choose which trend that you can explain will be most representative of the next 4 quarters. Again, you're not trying to guarantee it. You're just saying you just want the one that's going to be most representative. And here, obviously, we all decided that it was this trend after the merger, right? So see this, the formula for the linear trend over this period of time is given right here, 29.883,605. So what I might do is I'm gonna say I want to predict the next 4 quarters. So I would do this. Here, I'll make a copy. I would make a copy of your data tab. I think you already have it, a forecast tab, but I'll just call this forecast. And then, so I'm just going to add in, I'll insert here if it's not here. I'm going to add in my time period. So this is 1, 2, 3. This is literally the time series index. Okay, so quarter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? They represent each one of those things. And so I want to forecast quarter 27, 28, 29, and 30, right? And so I'm going to make this, I'll say de-seasonalized. So I have my de-seasonalized data. Now, Southwest Airlines, I thought was subject. Southwest Airlines was subject to seasonality, right? So I'm putting this de-seasonalized data because whatever I do with my model here, with the linear trend, it's always going to be a de-seasonalized prediction because the linear trend cannot account for that variability in each quarter, right? We remember that. So I'm going to be making my de-seasonalized forecast. What I want is, of course, I want the seasonal ones. So I'm going to make those yellow here. And this is going to be quarter 3, 4, 1, 2, and this is going to be 2014 here. Okay, so 1, 2, 3. So I'm just making some space. So I'm going to predict the de-seasonalized, and then I'm going to seasonalize it with my seasonal indices. So I'm just going to put my SA adjustment here. It's like, what do I need to adjust for seasonality here? It's going to be the forecast. Okay, and then so I said that this is going to be the trend, yes, that I think is most representative. And again, I got this trend over this whole period here. So the X actually represents the time index, 1, 2, 3, 4, 5, 6. Okay, so I'll just copy this. And by the way, this is in my screencast. So there's a screencast here. So don't feel like you have to, you can go back to it if you want to. Okay, so I'm going to put that over here. Oh, that didn't work. My copy and paste, ever since I moved to Mac OS Tahoe. Yeah, use Windows. No, it's just like, yeah, it just, the cut and paste doesn't work like it used to. I just can't get it to work. Okay, I might have to copy and paste it with a picture. There it is. Okay, so I just took that formula and I replaced the X. I'm multiplying it by, this is X. See, it says T, but it's X. The time period there. So this is simply extending the linear trend 4 periods. Okay, it's literally seeing this line here. I'm just extending it 4 periods. By the way, you can do that in Excel, but it won't give you the values. If you double click on this, you see it says forecast right here. Forward, backwards, so I could forecast it 4 periods. And see, there it is. So these are the values right there. That's the values that I've just calculated. On the line, they're on the line. Okay, so that's this. That's these 4. So what I need to do is I need to adjust them for a seasonality for quarter 3, 4, 1, and 2. 3, 4, 1, and 2. So in my seasonal, I have my seasonal indices here. There's 3, 4, 1, and 2. Now for conveniently, Megastat, if you use Megastat to do the seasonal, see it has the seasonal indices right here. It already has them here. Quarter 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Right? And so if I want a 3, 4, 1, 2, I'll just start here. 3, 4, 1, 2. It just saves me some trouble of having to put them in. So I'm going to put those over here. Did I not get that right? Let me try that again. I didn't. 3, 4, 1, and 2. Try that again. Okay. 3, 4, 1, and 2. And then remember, so to get the, just to know why we're doing this, to get the deseasonalized value, I took the seasonal value and I divided by the indices. That adjusted it to make it all average, right? On that. So if I want to take if I have a deseasonalized thing, I can seasonalize it by multiplying it, right? Just doing the opposite. Multiply. So I'll take that and I just say equals that times that. Boom. And there's my seasonal. There it is. Done. Naive forecast. Right? Again, but we know the quality of this, right? It's useful for just setting expectations. It's not useful for telling us how accurate and reliable, with an accuracy and known reliability of what our values will be. It just kind of tells you if everything stays the same, then this is what we'd expect, which is interesting because if we actually compare this to what we get later on and we didn't get this, then we know, oh, something changed, right? And then we can go back and look like, why didn't we get what we expected? Which is exactly the way they use these kinds of forecasts. It's always nice to plot this just to let you know so you can see. Visuals are always important, right, to interpret our results. So I'm going to take these values here. I just created a new column and I moved them over and I'll call it forecast. And you can select your whole time series. You can select both of these now and then just do an insert line like their graph, right? And there it is. Now, if you don't like the little gap, which I don't like, you could take the previous period before and just copy it over and it connects it up. And there it is. Okay? There's my forecast. I'm not going to put error bars or anything on there because they're meaningless, right? Error bars wouldn't mean anything. The variability in the past is not necessarily going to be the variability in the future. I have no idea, right, of what that is. Okay, so you guys get together in your groups, do your naive forecast, okay? Don't worry about getting it perfect. Just get one. You can go back later and do it again if you're not happy with the result, okay? And I'll come around and help. Yeah. You want me to come over? I'm coming over. Yes.
So now for the Costco case,
yes,
we have 4 trend lines. So
yes, you need to
now,
pick which one or which ones you think most representative of the next 4. For Costco, it's probably the last one.
Yeah.
Right. And as long as you know why. Do you know why you got that trend at the end? What changed? What made that thing?
Well, we don't agree.
Okay, that's okay. Why don't you guys just choose one for now and then investigate this more later before you turn in your FP1. Okay? Yeah, so pick the last one. Pick the last one. And then let's just do the forecast.
Okay.
So you know how to do it. You can go argue about which is the why that is later. Yeah. So which trend are you guys going to use? This one. Okay, yeah. So get the formula, put it in there, and you don't have seasonality, so you don't need to multiply the seasonal indices. That is your forecast. Very easy. Just do it. Yeah, and plot it. And then you're done with the, yeah. So which trend are you guys going to use? Uh-huh.
It's after before COVID.
Yep.
And after
Yeah.
after,
So this one?
yes.
Okay, but that's like sharply increasing revenues. So you think it's going to tend to sharply increase? I know. It's scary because you don't really think that's going to happen because it could. You see that in the past, it's really changed, right? But if that's the best you can do, that's the best you can do. So yeah, go for it. As long as you know why that was the rate hike, right? Yeah. So go for it. So make your forecast, and you don't have to worry about seasonality. So just done. Okay, which trend are you guys going to use? That one? Okay, that sounds good. And you know why that made that change there? What happened here?
This is the correction happened.
Okay. Okay, good. So go ahead and do the forecast. And you guys do have seasonality, right? So don't forget to add your seasonal, like I did, and make a graph. And that's it. You're done. That's it. You know, that's it. That's exciting, right? This is far best you're gonna do.
If Netflix have no seasonalities,
Yes.
whether we consider
You don't need to.
we don't need.
No, I mean it's pointless because look at the adjustments. They're so small.
Yeah, it's so small.
You're not going to get much difference.
Yeah.
Look, I mean, the values here multiplied by that are going to be almost the same. This is what we mean by not notable change, right? But you don't expect seasonality. So
We don't expect because it's only 1-2%.
even if you consider it, it's not going to make a difference. Yeah. So why bother, right? Yeah. Don't consider it. I wouldn't consider it because you don't expect it. All you're doing is we call adding noise. Yeah.
Yeah. So, and this is how I do it first. So first is I use here that I break it down as I mentioned.
Yes.
That I use this
That one.
formula.
Mhm.
Yes.
Use that formula.
Yes.
Mhm.
And, to create this.
Yes.
And then
Multiply by the seasonal indices.
Next is I use this one.
Yes.
1, 2, 3.
Yes.
Then I put it here.
Yes.
And I can click this and it will become.
Yes. And if you want to connect, you can copy that to that. Just make a copy of this one. That one. Copy that to that. There. Oh, no. A copy of value. Okay, there. Okay, good. Beautiful. So it kind of looks right.
They're done, I'm not.
You're okay.
Let's
Okay.
explain it.
That's fine. That's fine. We all learn from each other here. It's good. You use the last one. Right. Did you? Now, the question was you had that one point at the end, right? That was a little unusual, like outlier. You might want to ask, did that affect your trend? Like if you didn't have that, would the trend be different?
Yeah.
And so you might want to try removing that and see if its slope changes.
Yes.
Yeah.
Cái này có thể ăn vào này, bỏ cái này á.
Now you have. Well, here you have. Order four. Oh, there. Page 128.
So for example, bank of Hawaii,
Yes.
we don't see for the seasonality. So when we do the forecast, do we need to put the seasonality? We just pick the
No,
the
no. If you don't have seasonality, you don't put it in.
So
Yeah.
so it means
I
don't
did
need-
the
I
no,
don't need to use the seasonality.
no. It wouldn't make a difference. Excuse me. Even if you did, the difference between the seasonal and non-seasonal is very small. So, but you don't expect it. So why put it in? So no. So the forecast will look just like a line. Only the trend component is right. Yeah. And the irregular component you already took care of by choosing the trend, right? Yeah, that's it.
So now the question is why we use the left side like. Yeah.
Okay, so. Yes, what
So you guys got your forecast?
Yes.
Okay. So go take some notes and put it in your FP1 exercises. Yeah. So you can have that for later. Yeah. You guys got your forecast? Yeah. So take your notes in the graph, put it in the FP1 exercises, make some notes so you have that for later. Do you guys have the forecast?
Make another option.
Okay. Okay.
We choose
Uh,
that.
Yeah, right. I know because you're nervous about that, right? But because yeah, that looks weird, yeah. But again, that's why naive, right? Yeah, very hard. So write up some notes and put in your FP1 work exercise document. So we have that for later. Yeah. And you guys got your forecast?
Yeah.
Yeah. So
it means that if we delete this quarter,
yes, it changes.
consider that outlier.
Yeah.
The slope might be steeper, right?
Is it more like the gray one or more? No.
Yeah. Might be steeper.
Is the slope how different? Like a lot different or a little bit? Yeah.
Yeah.
So can you explain that one point though? What was that? Can you explain it or no?
Yeah.
What is it?
Membership rate.
Okay, just at that time, but then later, no.
So like get into one.
Okay, so good. So that might be an outlier. And since you can explain it, maybe reasonable to remove it because not representative of the future, right? So you don't want it to overly influence the trend. So you take it out. Yeah, that's it. That's it. Yeah. And then put your seasonality in, make your forecast, then take some notes, write them up in your FP1 document. So we'll have that for later. That's all. That's it. They're done. That's FP1. We're done. Yeah. Okay, try to make some notes for your FP1 so you don't forget, right? You can make your notes on your Excel spreadsheet or in your FP1 exercise document. Because at some point you'll have to write up answers to everything. Okay, how are you guys feeling right now? Are you feeling like you're in a good place to end? Yeah? Hungry. So I suggest we go to lunch a little early. Yeah? Come back a little early. We have a lot to do. It seems like you enjoyed doing FP1. Yes? Not so bad, right? Good. Now we need to see if we could get to the next part. All right. So I'll tell Mai we should end class. So let's go to lunch. Huh? Yep, she's not here. Okay, guys, let's go to lunch. I know you guys want to keep working on it, but let's go to lunch and make sure we come back by like 12:45. Yeah. Because if I say 12:45, you'll come back at 1. If I say at 1, it'll be 1:15, right? So 12:45. Yeah. Sorry?
Shall you have one with us?
Yes, I'd like to. You know a good place? Just down here? Okay. Why not? Easy. Yeah, sure. Let's go. They're going to lock the room. Yeah. So get out. Go. Go. Hmm. Oh, God, I thought I was really loud. You're in the front too. Oh, is this better?
Oh.
Okay. Well, if you need, I'll speak up. Okay. The recording. I probably have a recording of this somewhere. I don't know. But in any case, so let me ask you this. If we didn't make this assumption, then what would this do to our results? Let's just say that I ended up selling out some days. It's going to bias, right? It's going to bias the average number of mangoes that I bought, right? That it's going to bias it downward, and that the average number of mangoes, probably the demand for mangoes might be higher than what I would be estimating here, simply because I sold out sometimes and I could have sold more mangoes, but that increased demand was not accounted for. Yeah. See how easy it is to. So again, assumptions are very important. Checking your assumptions are also important. Yes. But let's go ahead and just say, like, I think we're fine here, right? But we should note that. Just make a note. Got to assume that did not sell out. Because if it's not true, our results will be unreliable. Don't you agree? Yeah. Okay, so the next thing we want to do is, okay, so we figured out the demand. We actually have the demand for the number of mangoes if it were normally distributed, mean standard. Again, if we think that that's a good enough, if we think that's a good enough model for our demand, we'll go ahead and use it to figure out how many mangoes we should bring, okay? We'll get there in a minute. But before we do that, some unfinished business. We said actually the demand for mango is binomially distributed, yes? Now, that actually provides some interesting information for us, right? What was N again? That was the traffic that comes to our booth, right? The number of people, that we expect on average. And P, that's also useful information. The probability of somebody's going to buy a mango. Desirability, right? Our mangoes. We would like to know what that is, right? Yeah. Can we get that? Sure, right? Via the approximation to the normal distribution, we can actually approximate what those things are. So we just reverse it. Here it says for the binomial, the mean is N times P. N is what we want, the number of people. P is the, right, probability to buy mango. The variance, or sigma standard deviation squared, is N times P times 1 minus P. We already know what that is. 50, that's 1.83 something squared, right? Yeah. We have two equations and two unknowns. We just solve for them. Yeah. Okay, let's let it do it, right? Like I said, let it do all the work. We just need to check it does it right. Yeah, that's all we care about. Don't just trust it. Always check. Yeah. So we look at this and it says, okay, for the variance formula, it does this, it does that, it does that. We get that. So the probability that somebody buys mangoes is 0.6964. Hey, didn't we actually sort of guess that maybe around? Not bad, right? Our intuition, not too shabby. Yeah, right, there we go. So now we know the probability somebody buys a mango. Again, under the assumption that it doesn't change, not much variability in that. And then N, the number of people, we just take that and solve for N, 71.8. 71.8. Of course, that's not the number of people. Now, we could consider that the average number of people that come to the Academy of Fractional. If we don't want to, we could just round it to 72. So approximately 72 people a day come to our booth. Not bad information, right? Don't you wish you had that for your coffee shop? Now you know how to do it though, right? All you have to do is say, in the last 10 days, how much coffee did I sell? Maximum and minimum, right? Not my heart, right? Piece of cake. Yeah, right. You don't have to keep track of. You could look at your receipts, right? You don't have to even count. So, okay. Okay, that was fun. I told you this was fun, right? That's why I like this one a lot. So you're starting to see the power of being able to assume an a priori distribution, and now we can start to use it to get information that could be useful. Again, that information is only as reliable as our assumptions are reliable, right? Yeah, always keep that in mind, right? Assumptions is only as good as our assumptions. You can't prove your assumptions. This is the main thing that you can do that AI can't do. AI is not good at judging whether your assumptions are good or not. That is only something that you as a human being, relative to your problem and situation, are going to be able to do. ChatGPT may be helpful in guiding you, but I would never trust its judgment, right? Because it will always judge things based on what seems to be the closest match. And the closest match is not always really, appropriate for what we want. Okay, let's do some work here. And let's see, 2:09. We're doing good. Yeah, if you need to take a break and go to the bathroom, please do that. We will take a break after this problem. Okay, but just if you need to go, go. Okay, so what do we know? We know that it says our spouse forces us to bring 55 mangoes to school. What is the probability that we'll sell out before? So our objective is to try to figure out how many mangoes we should bring. Yes? So let's try to get a feel for, like, if we brought 55 mangoes, will we sell out? Right? How likely is it? Now, again, the answer is never going to be yes or no, right? It's only going to be a degree. So in some sense, we're kind of getting the probability that I'll sell out is like how much confidence that I'll have if I bring 55 mango, I will sell out. How confidence would be how frequently it is true, right? That I sell out, yes? So we're starting to answer that question about not will I sell out or not, but how confident that I am that I will sell out. Make sense? Yeah? And then we can determine for ourselves whether that level of confidence is enough to justify bringing 55 mangoes, right? Okay, so how do we figure that out? We need to figure that out. Well, let's set this up as a probability problem, right? So let's just say D, let's make D equals demand for mango by 4 p.m. Mango sold by 4 p.m., right? That's what we care about, yeah, every day. And so we want the probability, we'll just call that P, the probability that the demand something, 55. Why do I put the question mark here? Well, we want to know we sell out, right? We will sell out before 4 p.m. if the demand is what compared to the number we bring? Higher, right? Yeah, actually higher than or equal to, because if I sell at 55, I'm still sold out, right? So we'd say greater than or equal to 55, right? Okay, so how can we figure that out? Well, we assume that the demand is normally distributed, right? So we have a probability density function that we can use to calculate this, right? Let's see what that might look like. I'll put it on the board here. Okay. So here's our normal distribution, right? Yeah, our probability density function. Mean is 50, right? Standard deviation, you can think of standard deviation as kind of the belt, like how fat it is, yeah? So sigma equals, what was it? 3.9? 3.89? Now we're being really precise. Okay, whatever. It doesn't matter. Just 3.89. Okay, 3.89, right? And what we want is we bring 55 mangoes. So this is about 4, right? Is over here. So this would be 54, right? Right? And so 55 would be maybe over here. Yeah? So we bring 55 mango, yes? And so we want to know what's the probability that the demand is more than or equal to 55 mango, right? So here's 55, 56, 57, 58. We want this. We want this area under here. Remember, the area is the sum of all the things after it, yeah? Okay, that's great. Now the problem is that the formula for this is a little unpleasant. Where is it? Don't worry, I'm not going to ask you to do this. Let's cancel that. Where is it? Here it is. Okay, so the normal distribution, see this? That's the probability density function. It's kind of hard to see. It's like 1 over square root of 2 pi sigma e to the minus. It's a little unpleasant, right? And to actually figure out what we'd need to do is we'd have to take the integral of this from 55 to infinity. Okay, so I don't want to do any calculus, do you? No, but it turns out that Excel already has a way to calculate the probabilities of the normal distribution. Okay, so it's a function. Let's go to our data here, our sheet here. If you go to mango demand here, make that bigger. And mu, okay, so mango demand, mu is our mean, our standard deviation 3.89. X is going to be the value that we want to compute the probability of. It says the probability that demand is less than X is going to be equal to, see, it says norm dist. See this right here? Norm dist, normal distribution. You give it the value that you want to calculate that's less than, give it the mean and the standard deviation for that normal distribution, and then you say cumulative equals true. Cumulative means the sum of all the stuff before it. I'm accumulating, right? That. So the norm dist function will give us the probability that the demand is less than X. Oops, that's not what we wanted. We wanted the probability that's greater than or equal to, right? Yeah. Well, how do we get that? Well, I mean, here we notice this. The probability, this is the probability that is greater than or equal to. That means that all this stuff here must be the probability that it's less than. Yeah? So if I know the probability, that plus this is 1, right? So if I just look at, again, just like our basic probability that we were looking at on session 2, same thing. If I can get to it. 1 minus the probability, 1 minus the probability that the demand is less than 55. Isn't that right? Yeah, just flip it around. And that's going to be equal to 1 minus the norm dist of 55, mu, sig, true. Right? That's the formula. Ooh. There we go. Okay. Right? And so I did that right here. So I take this, 1 minus that is the probability that it's greater than. Oh, but wait a second. This says greater than. Why not greater than or equal to? Well, because they're the same thing. Let me see. Oh, 55. There, put 55 in there. Yeah, thank you. 55. So it's 0.09933. Good observation. 0.09963, whatever it was, or approximately 10% of the time we will sell out. Okay, that was easy, right? Yeah. Well, okay, so 10% of the time, that's, that means I'm not selling out a lot. Does that seem a little weird? Look, the average number of mangoes per day I sell is 50. If that's normally distributed and that's 50 is the average, right? Then what's the probability if I brought 50 mangoes that I would sell out? It would be half, right? 50%. Remember 50 is right here in the middle, 50% above, 50% below. So 50% I would sell out, 50% I'd not sell out 50% of the time, half and half, right? So if I bring 5 more mango, think about this, 5 more mango, that probability goes from 50% to 10%. Doesn't that seem a little weird? It's only 5 mango. 5 little mango. All of a sudden I go from not selling out. Well, that's because the data, it's because, look, see the standard deviation is 3.89, right? If I'm about 4, if I have a standard deviation of 4, notice that almost all of the area under the curves, let's see, if I go from like 3.8, 1 standard deviation, let's say 1 standard deviation below or above here, that's like over 60%. 1 standard deviation. 2 standard deviations is like 99%, right? 3 standard deviations like almost 100%. Yeah. So it's because of the fact that the distribution does that. It's not flat, right? If it were flat, then bringing 5 more mangoes wouldn't make that much of a difference. It wouldn't drop it as much. But it's because, right? Yeah. Which goes to show you that it's kind of important that you get the model right. Yeah, it does not right, but good enough. Yes. If this does not really represent well the demand for mango, then our answers are not going to be very good, right? Yeah. So again, your intuition may be wrong on things. You may think by bringing 5 more mango, who cares, right? But if I bring 5 more mangoes, according to this, as long as I believe in this model, right, it means that my probability goes from 50% to 10%, meaning that I'm not going to sell out. I'm very unlikely to sell out, yes? I bring 1 more mango, 56 mangoes, it's going to drop down to like 1%, yeah? Even worse, yeah? Got to bring 57 mangoes, then I'm never going to sell out, right? Okay, so maybe I shouldn't bring 55 mango, right? Not if I want to sell out. So I haven't answered the question, how many should I bring? Of course, I could play with this. I could take 55, 54, 53. I could keep kind of playing with it until I get to a confidence level that I'm comfortable with, right? Like if I want to sell out more than 50% of the time, I'm going to have to bring less than 50 mango, yeah? So maybe I'll just keep bringing less, and less until I get to a level that I'm comfortable with. Like maybe I want to sell out 90% of the time. I'll just keep going down, 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 down until I get 90%. It will do that later, but right now, let's just do the opposite here. Let's look at what's the probability that I won't sell out by 4 p.m.? That's pretty obvious. We already know if we're going to sell out with 55 mangoes at 10%, then we're not going to sell out 90% of the time, right? But let's just do it more formally. We already figured that out. We want the probability that they don't sell out is going to be less than 55, right? And again, the thing to remember, I don't know if this is important or not, but this is the same thing as the probability that demand is less than or equal to 55, right? And that's the reason why that, and this is the normal the norm dist function doesn't calculate the equals to for anything, because the probability that it's less than 55 is probability that the demand is less than or equal, equal 55. So if I take the probability is less than 55 plus the probability that's equal to 55, that's the probability is less than or equal to 55, okay? But remember what I said about the normal distribution, or any continuous value distribution has infinite number of values. What's the probability of any single value? 0, right? So these are actually equal, right? Yeah. So that's just going to be norm dist true here. Which we already have over here, which is 0.9933. Or about 90% of the time. Oh, is it 99? No, 90. We won't sell out. Okay. We call that an overage, right? We have an overage of mangoes. If we do sell out, we had an underage, meaning we didn't have enough. We could have sold more, right? Okay, it still didn't answer the question, right? How many mangoes should I bring? Yeah, let's see if we can kind of hone that down a little bit. I know I shouldn't bring 55. I know I shouldn't bring, but let me see. What if I brought between 35 and 65 mango? Okay, so we want the probability of 35, but less than 65. And again, I don't care. This could be less than or equal to. Doesn't matter. Less than or equal to is the same. Just kind of curious, but okay, so how do I figure that out? Well, same thing here. What is it, 65? I probably should have chosen a better one, but 65 is like way over here, right? And 35, 30, there's 10, 30, 35 like over here, right? So we want all of that. Now, this little bit plus this big part plus that little bit is 100%, yes? So it's not going to be very much. It's going to be really small, yes? So what I could do is I could figure out how much is this, right? Well, how do I figure that out? And I can subtract it from that. And maybe an easier way to think about this is I can only calculate things to the left using Excel, right? Calculate things to the left. So I might calculate the probability that it's less than 65, which will be all that, right? But it's also going to give me this too. Yeah. So this less than 65 is all of this, but it's too much by that. Yeah, I overcounted by that. So I take this bigger part, but I can calculate that to the left, take this part and subtract it from this part. That will give me that middle part, right? All right, let's just write it out. The probability of the demand is less than or equal to 65 minus the probability that the demand is less than or equal to 35, right? Again, this big part here, all of that minus that part is that. Oh, sorry, that. Forgot the other little part there. In any case, we don't expect this to be very much. Tiny, right? A little bit, yeah? So the probability that it's less than 65, well, let's put that in here, right? I'll just copy that. Okay, minus 35. By the way, 35, see it says it's 5.761 e to the minus 06. That's 6 decimals, 0.0005716. It's very, very small. It's like almost zero, right? But nonetheless, I'll put it there anyways. Oops. It's not even worth doing the calculation, but I'll take it and I'll put this into Excel. There, 0.9988, whatever that is, very close to the same thing. Oops. That should be right here. Okay. Okay, so we're going to sell out about 99.99. So about 99.99% of the time, we're going to sell between 35 and 65 mango, right? Okay, so I should bring between 35 and 65, right? Still didn't answer my question, right? How many mangoes should I bring? Yeah. The reason why we can't answer this is that we've forgotten something. There's something important that we need to do. To answer the question, how many mango I should bring, I need to have a goal that I'm trying to achieve, right? Because if I just ask you, how many mangoes should you bring? And you say, to achieve what? Like, right? Okay, if you want to sell out, okay, you have to tell me what level of, how likely is it selling out would be comfortable enough for you to say that you're likely to sell out, right? This is very important to understand this. Later on, we're going to do this a lot. Oftentimes, you will have to set a goal for what it is that you mean in terms of confidence in what you are trying to do, in what information you're trying to get. So, and that goal that you set will be arbitrary. Please listen to that. It is arbitrary. It is what confidence level is enough is what you decide is enough, right? Yeah. We're never going to get 100%, by the way. We can certainly get close to it if we want to. But if we go for 100%, that's going to be extremely conservative, right? We know that's going to end up having us bring a lot fewer mangoes than we want to sell, right? If we go too aggressively and say like we want to sell out like 50%, I will be able to bring more mango, but then we're not going to sell out that frequently, right? So we have to decide sort of a compromise. At what level do we think would be reasonable, that we're not being too aggressive, but not being too conservative in that we're, that we're still selling out with a high likelihood. So what do you guys think? So the problem here, it says, the next problem says, I'd like to go to the gym. There's my goal. I want to go to the gym. And I'm going to choose, I want to have at least 90% chance that there won't be any left over. In other words, I'm going to only want to have to miss out 10% of the time not selling out. So there's my goal. So what level, how many mangoes should I bring so that I sell out at least 90% of the time? I notice I said at least because we may not be able to achieve exactly 90% of the time. Again, that level is arbitrary, right? I mean, why 90%? Well, because to me, that seems good enough. It's not too aggressive, right? It's not too aggressive. I won't get yelled at too much for not bringing enough mango, but it's good enough that I'm not going to miss out on going to the gym that much, right? Yeah, so I'm willing to tolerate 10%. Get it? Remember this, because you probably have heard this many times in your stats class. You know how when you're like, they talk about like when you do hypothesis testing, which we'll do later, they talk about, oh, you need the p-value must be less than 5% or 0.05, right? Or you need to be at least 95% confident. You've heard this before? That magic number, 95%, 0.05, those numbers are arbitrary, right? You just need to understand why you pick whatever values you want. You just have to understand what those mean, and then you pick them. Okay, so there's no law, statistical law, for example, that says that 90% means you're high confident. I just chose that 90% is high enough confidence for me. So similarly for this other thing, so when you hear the p-value must be less than 0.05 or something like that, again, that's just because we just sort of chose that to be good enough, right? All right? And understanding the trade-offs that you make. All right, so how do we solve this problem? We already know how to solve this problem, right? We know how to solve this problem is that, okay, do we know the number of mango? If we want to be 90% sure, right? 90% sure that I sell out, should I bring more than 50 or less than 50? Less, because 50 would be 50% of the time I sell out. If I want to increase the selling out, I need to bring less mango. So less mango will increase the likelihood of selling out. So I know that whatever answer I get here is going to be less than 50. I actually have to know I could take 50 minus the about 4 there, right? And that would drop me down to maybe 10% or something like that, or around 10%, because we did that before, right? So if I take 44 mangoes, right, then it might be around 10%. So what I could do is I could just keep putting in this value less and less and less until I get the probability of 10%, right? That's one way I could do it. Of course, we could just calculate this directly. This is called the inverse probability. In other words, instead of given a value, what's the probability? I could give it a value and say, what probability would I have that would give me that value? You know, what value do I need to have that give me that probability? So instead of calculating the probability, you give it the probability and say, what value do I need to get to have to make that probability? So that's calculated directly by the norm in function in Excel. So let's just set it up to make sure we're doing it right. Okay, so here we go. We want the probability that the demand is, now what do I want? I want it to be greater than some value that I want to figure out, right? some value that I know is around 44, right? Somewhere around there. Maybe it is 44 for all I know. Somewhere around 44. I want it to be greater than that, or let's say greater than equal to, right? Greater than equal to that is equal to 0.9. Actually, not greater, it would say greater than or equal to 0.9, right? Now, there's the probability, if I bring this number, the probability the demand exceeds that is at least 90%, right? Now, the norm in function only calculates things to the left, right, for it. So we need to convert this to a problem to the left. But that's not hard for us to do, right? Here, I'll just wipe that all out here. I don't think it's very hard for us to see this. So I'm going to be somewhere over here, right? That's the thing I'm trying to figure out. We think it's around 45. And so this is where it's greater than, the demand is greater than that thing, 90%, right? So if it's 90% here, then less than this must be 10%, right? 1 minus that. So 90% here, 10% here, right? So that's the same thing as saying the probability that the demand is less than this thing is less than or equal to 0.1, right? Okay, so we can actually figure out by the norm in what this is. We could give it the 0.1 and it'll tell us where it's exactly equal to that. So that's right over here. See the probability, give it the probability is 0.1 right there, 10%. The probability of the demand is less than that, something, X, is equal to 10%, would be 45.014, whatever that is. Okay. Okay, you guys ready to put your thinking caps on? And then we can take a break. Okay, so 45, but can I bring 45.0147466 mango? I cannot, right? This is exact, and so notice that this is the number of mango I need to bring exactly to get exactly 10%, yeah? But I don't want exactly 10%. I can be less than 10%, which would make me greater than 90%, right? Yeah? So how many mangoes should I bring? I need to round this, right? 44, 45, 46. Should I round it up or round it down? Round it down, right? Because less mango means more likely to sell out. Increasing this, right? Decreasing that. So yeah, so I don't want to round it up, right? I want to round it down, always. Okay, so I round it down. Round down to 45 mango. So we get actually, and then we can calculate the probability that the demand is greater than or equal to 45 mango is equal to, so just put 45 here, right? Is 9949, right? Oh, sorry, 945. Sorry, I put it in the wrong place. 45. 90. That's right. That's better. Okay. Beep, 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 beep. Okay, put that there. Okay. So, and that's it. So that's problem solved, right? So this is greater than 90%. Just a little bit. That's all we needed. So bring 45 mango if I want to be 90% confident, yeah? All right, so that's the end of this problem. The next problem is for extra credit. You do not need to do it, but I promise you if you do it, you'll find it really helpful. it provides lots of instructions on exactly what to do. The goal that we sought here was to sell out 90% of the time, which was kind of arbitrary. Maybe a more realistic goal would be to make the most money, right? Instead of like selling out 90% of the time so I can go to the gym, let me just try to bring the number of mango that economically makes most sense for us. And so to figure this out, we need to, so if our goal is to make the most money, we need a little bit more information, right? We need to understand like how much does it cost to have a leftover mango, right? Or the marginal decrease from having an overage, right? And then we also have the opposite. We want to know how much does it cost for us to not have a mango that we could have sold? And that's usually the cost of the mango, right? I mean, how much you sell for the mango, the profit, yeah? And then what we want to do is, relative to the demand, we want to balance out we don't want to lose more from bringing too many than we would from not bringing enough. So we'd want them to be exactly equal. The expected amount that we would lose from bringing too many should be the expected amount for bringing too few. If we balance those expected costs or losses, right, making them exactly equal, that will tell us the exact number of mango that we should bring that will give us the most. So this problem will take you through that if you want. And this is the way that Anne figured out how much money should be kept in the teller machine and how much central, stuff like that. So this is optional, okay? So you can do that for extra credit. Let's take a break now, and then when we come back, we're gonna do some quick finishing up of session 7, then we move on to session 8, okay? Break time, like, 5-ish minutes. I told you it's a long day, I'm sorry. You guys are troopers. Yeah.
Previous cohort, how did you organize this course? Just like 6 days and then it's all consumed.
Previous cohort, meaning like Hanoi? Or last year?
Previous year, not just last year.
I don't remember how it worked last year. I didn't organize the course. This was given to me. They said, this is your schedule. Yeah. Yeah.
I've been studying statistics.
Yeah.
Calculus in the university in advanced.
Yes. Yeah.
This is great. But it's too much. I mean, here, around 6 days, and all of this is like impossible. And it's like,
Well, the good thing is I don't ask you, you don't have tests, right? And you get plenty of time to study after, to digest it. So after the class is over here, you're going to have like 2 weeks to finish up, and you have before this, you had several weeks.
makes you rich.
1 week? Is it 20th? Well, if you're not counting vacation, no.
And
I don't know. I don't like the schedule either. Sorry.
I want to be the better.
Yeah. Just tell them that. So that the schedule is not good for.
Of course, we can self-study, but the place we're going to have more time with you. And of course, we will be different.
I would like to have more
to ask
time.
questions.
No, I didn't get the schedule. I'm sorry. I do the best. I think I organize the class as best I can from the schedule that's given. Yeah, I always argue with them about this, and they always tell me this is the best we can do. And again, oftentimes they say it's because of your schedule that has to be this way. That you BEMBA students can't afford to do more days, shorter time. Like I said, can we have more days, shorter classes, longer time between? And they're like, no. They said that you can't do it. You said you can't afford the schedule.
We really want to do a shorter period and more days. We can consume and digest all of this.
Please
So happy.
tell them that.
I will
Yeah.
definitely.
Please say that, look, this is, why are we organizing the schedule this way? It's not good for us. Yeah. And tell them the instructor tells us that it's not good for you also. I don't want to do it.
I'm only doing it this way because this is the schedule I was told we had to have. Yeah, so please tell them kindly that if other people agree, then maybe they'll change it. But unfortunately, it's too late for you. This is what we have.
For the next cohort, maybe
Yeah.
they're gonna benefit.
I mean, I suppose if you want, you could have some online classes next week, if that would help.
I believe that we all can do ChatGPT, AI, and self-study, but it's so much different when we were with you. And
Yeah.
especially face-to-face.
Really? Well, I'm glad to hear that. I prefer this too. It's much better. Yeah, it's quicker. You know, we have more easy interaction.
COVID is over, so it's not gonna be an excuse anymore.
I don't know. Yeah, I used to, like in years past, I would spend the whole week. It was a whole week. I think what we'd do is we'd have like 7 days with 1 day break in between. So it'd be like, have fun with the Burger Festival. Yeah. Burgermeister. So yeah, so we would do like Monday, Tuesday, break Wednesday, Thursday, Friday, Saturday, Sunday, or something like that.
They were so lucky.
Yeah, but it was still hard because, but they would always complain that since we only had like 1 day off, we didn't have any days in between to work. That you couldn't take your notes and write up answers. We didn't have no time for that. They always had to study for the next one. And the next.
I believe we also teach MBA at the University of
Yes,
Hawaii.
yeah, it's 1 day a week. For the
And how many weeks?
15. Oh, and they claim it's too fast.
Oh my god! And we are so rocket, right? They have 15 weeks, once a week.
Yeah, but they have more. They have other courses they're taking at the same time.
I know.
So they're taking like 3 courses at the same time.
But might I know how many hours a day that they do?
Oh, it's 3 hours each class.
3 hours, multiplied
Well,
15, 45 hours.
2.5 if you continue count break.
Of
Yeah.
course, we also count break.
Yeah. And you can see the material's kind of organized.
It's gonna be more, feasible.
Yeah.
Sorry.
I know. It's
Custom-
okay.
yeah.
No, I appreciate you telling me. I've
hope
given up
I
arguing with them because they just tell me that this is the way students work. And but in years past, everybody, they seem to do okay. Everybody seems to do okay. It's just a little
Not
more
just a-
stressful. Yeah. Or maybe people like you, they say we would appreciate it more had we had a better schedule. Maybe that's the better way to say it. Yeah, it's not like they didn't learn, but it's just that we would have liked it more.
Thank you.
Okay. That was a good tea break. Okay, guys. We are going to officially not do this problem here, not because it's not worthwhile, but we just don't have time. So I'm going to strike this one out for you guys. However, you are welcome to do it for extra credit if you want to. Number 5. So it's all about using distribution to determine whether data is fake or real, fraudulent or not. And yes, it's kind of the way that people really do check for things. It's one way. We need to do some utility problems. So utility problems are that now that we understand the power of using a priori distribution, because if we understand the model for our population, we can use that to get useful information by seeing that do we get what we expect or not, or just using calculated information. So one of the things that we often need to do is make that assumption of a distribution. Commonly, the distribution that we will assume is the normal distribution. And it's important to understand that we don't do this because things are normally distributed. We do it because that oftentimes we can use the normal distribution as a good enough representative for what we're looking at. Just like we did with the demand thing. Remember, demand was not normally distributed, right? We know it could not be, but we could approximate it very well with the normal distribution, which was good enough for using for our problem. Yeah. So when we do that, we're going to talk about checking if something is okay that to assume it's normally distributed. Okay meaning we're not saying it is normally distributed. It's okay for the calculational purposes that we're using it for to say this normally distributed, meaning that we're not likely to get unreliable results, right? Things that are too far off. That makes sense? So it's important that you remember this part because we're going to use it a lot. Yeah? And so one of the things that we do to see whether something is normal in shape is that there's kind of a rule, some rule of thumb that says it's okay. So when we check an assumption, again, checking an assumption is not the same as concluding something. When we check an assumptions, we're just trying to see if we have any reasons to see that it might not be valid. In the absence of any reasons to say it's not valid, we accept the assumption is valid. Is that understood? It's a little different than what we do like in a statistical thing where we have to like conclude something logically, and it's more like using the evidence to prove it. Here, we actually say lack of evidence means it's okay. Yeah. We're usually in statistics, we need to have enough evidence to say it's okay. This one we say, if there's no evidence, it's okay. I know it's kind of weird, right? But that's the way it works. So we're going to take a look at a couple of variables in our homes data, square footage and lot size. So square footage, we're going to ask the question, would it be okay for us to assume the data is normally distributed for the purposes of calculations like probabilities, things like that? Got it? Meaning that if we actually knew what the distribution of this thing was, and we did the same calculations, they wouldn't be too different, right? Make sense? Okay, so one rule of thumb for doing that is the easiest way is to check the skewness and kurtosis measures. The skewness and kurtosis measures, these are numerical summaries of the numerical summaries of the characteristics for the shape, being the skewness or kurtosis, which we talked about before. Like, you remember we looked at the box plot, skewed if the one side was bigger than the other, and we saw that it was kind of lopsided, right? And then kurtosis, how fat the tails are, those kinds of things. So the skewness and kurtosis are numerical measures of that. They're a little peculiar in the sense that that they're highly sensitive to outliers. I mean, so just like the mean is, there we go. Just like the mean, just like the mean and the standard deviation are kind of sensitive to outliers, so are these. Like one high value for the mean could make it biased, right? Or standard deviation bias. So kurtosis is all highly sensitive to outliers. We have to remember that meaning that an outlier is not a representative value, right? It's something unexpected. And so we wouldn't want to judge the characteristic of, say, skewness or kurtosis as the actual characteristic of our data if there were outliers, because the outliers could bias it in a way that we wouldn't understand if it was skewing it in a way that was really representative, right? So it would be unreliable to use the skewness or kurtosis measures if there are outliers, right? It would not give us a reliable view of what the skewness or kurtosis actually is. Make sense? However, the skewness, if there aren't any outliers, which is, if there aren't any outliers, or that we don't believe there are any outliers, we can the skewness or kurtosis of the normal distribution, ideally, in principle, is 0. No skew, it's completely symmetric, right? Left side, right side, same, right? And the kurtosis is 0, meaning that the tails, compared to, it's kind of hard to explain why it's 0, but technically it's actually 3. But because of the way people like to compare everything to the normal distribution, they subtract 3 from the kurtosis measure so that a normal distribution would have a kurtosis of 0, right? So it's just for convenience, and they'll see why. So if you see a skewness kurtosis between -1 and 1, when you calculate the skewness kurtosis between -1 and 1, then that is usually not. That's usually could be more explained by just sort of chance variation in your data. You know what I mean? It's not going to be, whenever we calculate the skewness or kurtosis from the data, it's never going to be exact, right? We're always making estimates of the skewness or kurtosis from a sample, right? And so it's never going to be correct, right? So between -1 and 1, most people consider that the same as 0, right? Because it's not too far off. But when you get beyond 1, then it's starting to get like, okay, that's notable. Beyond 2, definitely notable, right? So one quick check is just look at our data, and if it has a skewness or kurtosis between -1 and 1, people have studied this and have realized that the calculations that you make, assuming it was normally distributed, versus the calculations you'd make for even if it were not normally distributed, but still had a skewness kurtosis between -1 and 1, they're close enough. They're very close, right? So in other words, for calculational purposes, if you have a skewness kurtosis between -1 and 1, you might as well just assume it's normally distributed, right? Because the values that you get would not be substantially different. That makes sense? So the important thing I want to impress upon you is I am not telling you that if you see a skewness kurtosis between -1, that you can conclude the data is normally distributed. Not at all. It doesn't even provide evidence that it's normally distributed. It just says that if you're going to use the data, if you're going to use the normal distribution for calculating stuff, the probabilities, for example, and the skewness is between -1 and 1, then it's probably going to be pretty close to what the actual probabilities would be, even if it were not normally distributed. That makes sense? Okay. So it's a practical thing. If you don't see a skewness between -1 and 1, that doesn't mean you should give up and not say that I can assume my data is normally distributed, right? You don't just give up. You can go look further and try to figure out why is it between -1 and 1. And so if you see a pattern of something that indicates that it's not normally distributed, then you'd be like, okay, maybe that assumption is not very good, right? But if you don't see a pattern that is not normally distributed, and you maybe see some outlier or something like that, maybe you'd be like, yeah, it's okay, no problem. Yeah, because an outlier can affect those values between -1 and 1. Like one value could make the kurtosis like 4, And again, you wouldn't want to judge your whole thing just based on one value that may be, an outlier, yeah? Okay, well, so let's go do this for square footage. So I think if we just go over to here, we go to square footage. Now you can do this in Megastat also, but I have it done just on a table for you. So for square footage here, we see that the skewness and kurtosis are both between -1 and 1, right? So what would we conclude that the data is normally distributed? No, right? What can we do though? we can assume that it's okay to use the normal distribution, right? So I like to just say normal okay. Yeah, normal okay. Not it is normal, just okay, right? To say it's normal. Yeah. So in this case, we'd say normal okay, because it's between -1 and 1. If you had any doubts on that, you could investigate further, right? The usual tool for investigating normality is called the normal probability plot. It's not that complicated. I don't want to spend too much time explaining it. You can look it up. It's also in my lecture slides if you want. But basically, we look at what we call the z-value versus the z-score. The z-score is where we take the value, subtract the average, divide by the standard deviation. By the way, you can see the table here. This is how it's calculated. It's all here. So if you want to look at that, this graph here is calculated. We take the z-score, which is just the value minus the mean divided by the standard. It's like how many standard deviations above or below the mean am I? So it's called the z-score because it converts something that, if it's normally distributed, it converts something that has a mean mu, standard deviation sigma, into the standard normal, or what we call the z distribution, which has mean 0, standard deviation 1. If you think about that, you'll see that's what it does, right? And we compare that to what is called the z-value. The z-value would be, you know, what is the score if it were normally distributed? If this were a z-score, you know, the z-score for normally distributed would be, you know, 1, 2, 3, -1, -2, -3, okay? So the z-value versus the z-score. So that's kind of, in theory, if it were normally distributed, what the score would be, should be, and this is what the actual z is. So the upshot is this. If the z-score is equal to the z-value, right, we're going to get a line, right? We're going to get a line. If the z-value is exactly equal to the z-score, right, we're always going to get this line. So we look to see how much of a line does our data look like. That's it. That's the way people look at it. If it looks like a line, then okay, normally distributed. Not that it is normally distributed, but it's okay for us to assume because it's not far enough. What we do is we look for really pronounced patterns. We look for patterns like if this is not, that is not a serious not line problem. That's more like an outlier issue, right? Right? You can have a little bit of variation, but we're looking for something like a bend, right? Or a U, you know, really pronounced pattern. Got it? Not just one point's not on the line, okay? Outlier, maybe, you know, right? This is mostly line. If you want, you can add a trend line to this. And if you look at the R squared of that trend line, most people would say that if you get an R squared of over 0.9, that's good enough, you know, liney enough. Yeah, the line fits it. Again, that's a rule of thumb. You still need to look for patterns, right? So the key here is look for outliers and patterns. Outliers don't matter, patterns do, right? So we would go ahead and say for square footage, it's okay. Now, what's harder is to argue in principle why would square footage be normally distributed, right? So what we've done is empirically said it's okay, but in principle, where it's okay, it's a little harder to do. It's almost impossible usually. I don't know a really good argument myself. Maybe you guys could come up with something that would say that it's normally distributed. When most people try to argue data is normally distributed, they try to take advantage of a remarkable mathematical fact about normal distribution, is that if you take any random values and you sum them up, the more you sum them up, the closer it becomes to a normal distribution, that the sum will become a normal distribution. It's something called the central limit theorem. It's quite beautiful and it's quite powerful and useful, but for most practical purposes, not necessary for us to refer to, because we only care about practical normality here. We don't really care about theoretical normality here. It's very rare that you'd have to argue. So you might come up with some argument that square footage of a home is some sort of sum of things, you know, and that might may, in principle, argue. I don't know it. You know, maybe ChatGPT can come up with something. Probably not. Probably come up with garbage, in my opinion. Garbage will sound good, though. Any questions about this? Easy, right? So next time we need to check something is okay to normally distribute, the first thing we'll do is look at the, what two values? Kurtosis and skewness, right? We'll look at those. And then if those don't turn out to be good, then what will we look at? The normal probability plot, right? Yeah. Of course, you can also look at box plots and stuff like that too. That might be helpful also. But that's the two ways that people tend to look at. Okay, you guys got your notes on that here? Now let's look for lot size here. For lot size, again, I think lot size is a little more, in principle, I think I could argue that lot size would not be normally distributed, right? So let's think about lots. So what are lots? How do people develop homes usually? Usually you have a developer that gets a big bunch of land, right? And what do? Chop it up into lots, yes? And they put houses on it, yeah? Now, when they put up those houses, most of the lots may be about the same size, but they might have like luxury lots, right? Where they have some big ones. They might have some odd-sized lots here and there, right? But, you know, generally you're going to get a lot of repetition of the same ones. The size lot, the double-sized lot, the triple-sized lots, stuff like that. And that for that reason alone, I think that doesn't kind of lead to a normal distribution of lot sizes, you know? It leads to a very unusual kind of distribution of lot sizes, yeah? Right? So I think that on principle, I have some reason to believe that lot size would not be normally distributed. And let's go look empirically to see. Now, we're not going to conclude that it's not normally distributed. We're just going to put doubt that assuming the normal distribution would be okay. Got it? Meaning that if we did, we're probably not going to get good results, right? We'd be really suspicious of the results that we get. So we'll just go look at the skewness kurtosis. So we have a lot size. So here's lot size, right? And we look at the skewness kurtosis, and sure enough, wow, look at that. 4.8 skewness, 31.08. Whoa, that is bad, right? Huge kurtosis. That means that there's a lot of extremes. Like there are a lot of extreme things going on in the tails, you know, or one or the other tail here. Again, probably not that unusual for lot size, right? We probably have, you know, a number of unusually large lots, right? Not unusually, but, you know, we have, maybe some really large slots, right? Most of the things are not, but maybe have a few that are really large. Okay, but we don't give up. We go to the normal probability plot. And what do we see in the normal probability plot? Does that look like a line to you? No, right? If I add the line, if I add a trend line, look at the R squared, not over 0.9. But the more important thing is I see a pattern. Do you see a pattern here? It's like here and then there. It's like a hockey stick, yeah? I see a pattern here. Now, I also see an outlier here, but think about that. Do I actually know that's an outlier? Again, an outlier would be sort of unexpected, infrequent, unusually high or low value. Well, I don't know that that's unusual because I don't know what the distribution is here. If it were normally distributed, yeah, that would be unusual, right? But I don't know what the distribution. Maybe with this distribution, that actually is pretty expected. You know what I mean? That would not be unusual. I don't have a lot of data in this range here, you know? I don't have any data with z-scores or z-scores, you know, in this range here. So I have kind of a gap. So the question is, does the pattern kind of does look like it's going up like that, doesn't it? Right? Doesn't it look like that? Again, I don't know. Is that part of the pattern or is it not part of the pattern? I don't know, right? So again, don't conclude anything necessarily. So I wouldn't be able to conclude that that's an outlier. I wouldn't necessarily, and even if it were an outlier, think about this. Even if I didn't have that value there, I would still say not normally distributed, right? Yeah, because that doesn't look like a line without that. Yeah, it's still, right? Okay. Did I make my point about lot size and looking for patterns, not for outliers? Yeah. Okay, so I would conclude here not that it is probably not okay to assume it's normally distributed. I probably would not get good results. Yeah, so dangerous to do it. Don't do it. Yeah. Any questions on that? No. Okay. All right, so what are we going to do with this? Well, on the subject of outliers, which is, it's a rather important subject, but unfortunately, it's really much more in depth than we are able to tackle in the short amount of time that we have. I want to just give you more practical tools for dealing with outliers. The problem with outliers is that there is no formal mathematical statistical definition of an outlier. An outlier is kind of what an outlier does. Seriously. You know what I mean by that? I mean, if something looks unusual, doesn't sit from the pattern, and you think that it's unusual, it's an outlier. Simple as that. Yeah. The important thing about things like that is that you want to identify things that are potentially outliers that could be problematic, influential, right? And so we would like to be able to have some tools that help us identify things that could be possibly problematic. Got it? Now, again, just because it says possibly problematic doesn't mean they are going to be problematic. It really depends on what you're doing, right? However, in the presence of outliers, we do know that some things work better when there are no outliers, and some things, work better that if you do have outliers, they work better. I'll give you an example. Like if we're trying to represent the central tendency, of our distribution, the mean is oftentimes a good representation of the central tendency, the average, right? It's a good thing, but we know it's sensitive to outliers. So if I have an outlier or two in my data and I use the mean, that puts a lot of doubt, right? Because the outliers will bias the mean, and I don't know if it's biasing it in the direction of what the true mean actually is, right? Yeah. And because of that, it makes that measure unreliable, right, for that. And so I wouldn't want to use the mean to talk about my central tendency, the average, if you want to say it that way, because it's going to be unreliable. It may be more accurate on some things, but it's going to be, but if it's unreliable, it's not going to be that helpful, right? So I would rather, in the presence of outliers that I'm unable to justify ignoring or removing, I will use maybe a different measure of central tendency, like the median, right? So home sales are a good example of that. Often home sales, like in Hawaii, our benefactor, Scheidler, he lives in Kahala. Kahala is it's like Beverly Hills of Hawaii. Very expensive homes, right? Scheidler's home, even more expensive than that, right? Even by Kahala standards, his home is really an outlier. Yeah, like $200 million or something like that. He has like 2 houses on there. He's got several levels. Crazy, right on the ocean front. Yeah, I mean, he's a billionaire, of course, right? Yeah, that's why he could afford to give the college a few $100 million. Thank you very much. It wasn't anything to him. if we looked at average prices of homes in Kahala, we would not want to use the mean or the average of the mean price of homes, because Scheidler's home will skew it. It'll make it look like homes are actually even more expensive than they already are expensive. Yes, typically, yes. So instead of reporting average mean price of homes, we'd put the median home price there, in which case Scheidler's home being that large isn't going to make a difference. It's not going to sway it much either way, because it's not sensitive to outliers, 50% above, 50% less. That makes sense? Again, so we identify outliers as a way to determine whether we should use different statistical summaries or something like that, or perhaps maybe remove that data if it's justifiable. So let's look at so lot size is not, so let's try to see if we can identify outliers. Now, here's the interesting thing. If we can assume the data is normally distributed, then we actually have a pretty useful indicator of outliers. So think about this. Now, in a normal distribution, we know that within 3 standard deviations of the mean, or what we call 6 sigma, 3 standard deviations below, 3 standard deviations above, that 99.7% of the values should be within 3 standard deviations of the mean, the empirical rule. Again, that's literally just looking at a normal distribution and taking 1, 2, 3, 1, 2, 3 here, right? And the area underneath there, 99.97, okay? So it's not hard to realize that, but that's useful for us in terms of outliers, that if we see a value that is more than 3 standard deviations above or below the mean, that would be unusual, right? Yes? Because 99.7% of the value should be within that. So if I see something outside of that, happens less than 1% of the time, it should be like that. Now, of course, this is relative to the amount of data that I have. If I have 100 data points, sounds like it's raining almost, yeah. Okay, if I have 100 data points, then, is it the mic or something? Or? Oh, the air. Okay. Oh. But yeah. Okay. So let me ask you guys this. If I have 100 data points and the data is normally distributed, how many values would I expect to see more than 3 standard deviations above or below? Remember, 99.7 should be within 3 standard deviations. How many should I see outside of that, more than 3 standard deviations? 0.04 times 100, less than 1, 0. I should not see any, right? If I have 1,000 data points, maybe I should see, a few, right? Yeah, so don't take this too seriously. It's relative to the amount of data. So if I have a little bit of data, I should think, if I see a value, so I have 108 data points in my homes data set. I should probably not see any more than 3 standard deviations above the mean if it's normally distributed, right? Now, we said that square footage was normally distributed, right? Yeah, it's okay. So all we need to do is, if we want to see, are there any outliers by this idea, is we'll see, are there any values more than 3 standard deviations above or below 3 standard deviations, right? Yeah, that's all we have to do. And if we see them, then we say, okay, we'd investigate them as possible outliers. If we don't, we say, don't really see anything that's too notable, right? Okay, so go ahead and look at where is it? Digit demand, mango demand, lot size, square footage. Well, I thought I would have something, maybe it's under data, no? Okay, I don't have it. We'll just calculate it here. So let's go to square footage here. Here is the average. Here's the standard deviation, right? Yeah. So what happens if let's just calculate what we consider the limit for a high outlier and the limit for a low. Now, there's what value above this or what value below if we saw it. Yeah. So I'll say outlier low is equal to the mean plus 3 times standard deviation. And an outlier high would be the mean plus 3. I think I calculated this wrong. Sorry, this is 3 minus. Sorry, guys. I'm getting tired already. 3 minus. It was much worse in Hanoi because we were like 6:30 to 9:30. Yeah. Yeah. So outlier low, 410, outlier high, 310. So in other words, what we do is we look in our data, do we see any values that are less than this or greater than that? Of course, so what we can do is we can just sort the values, right? And just look who's low and who's, but an easier way to do it is just look at the minimum and the maximum. So I'll just say here, minimum is equal to, come on, stop that. What does it mean? Min, that's what happens to my fumble fingers. Min square footage. Remember we got named ranges because we made a table. So square footage is all the data for the square footage. Maximum is equal to the maximum of square footage, right? And all we need to know is this interval inside that interval, right? So 816 is larger than the low. So there's nothing lower than this. So no low no low outliers, right? And this value here, maximum, is less than the outlier high. So there's no high maximums, right? So by looking at this, I would say square footage, no indication of outliers. Now notice I said no indication. That doesn't mean there aren't any, but we don't have any indicators. We'd still want to keep an eye on our data, and if we see some value that looks unusual, we still might consider it an outlier, okay? Because remember, this idea of 3 standard deviations is kind of arbitrary, right? We only set it because 99.7% of normally distributed data. Does that mean, like, what if something is 2 standard deviations? Well, 2 standard deviations is also pretty high. 2 standard deviations, well, what is that? 97% of the value should be between 2 standard deviations. So if I see something beyond 2 standard deviations, that's a little unusual, don't you think? Yeah? So again, the level you get to pick, right? You know? Okay, any questions on this? Super easy, right? All right, it gets a little more complicated. It gets a little more complicated for lot size, right? So lot size is not normally distributed. So we do not have any useful indicator that would tell us how frequently we would expect a value above or below. Technically, what I'm saying is not quite true. There is a non-parametric, meaning I don't assume a distribution, way of looking at the mean and standard deviation, but I'm not going to resort to that. We're going to resort to another thing, another non-parametric indicator of outliers called Tukey's fences. Tukey was you can look him up. He was a rather famous statistician. He's the guy who invented the box plot for us, and he did many other really brilliant tools. He was really a master at being able to use simple tools for statistical analysis. Really amazing. But Tukey's fence is kind of weird. Tukey's fence says that if I look at the 3rd quartile and I look at 1.5 interquartile ranges, that's going to be called the upper fence. And any values above that may indicate an outlier. And I say may because we don't actually know what frequency this is because we don't know what the distribution is, right? But Tukey said that these values tend to be extreme, you know. We also can look at the low fence, which is the first quartile minus 1.5 interquartile ranges, right? The low fence. Anything below that would be considered extreme. You investigate for outliers. This is such a common rule that most box plots will use Tukey's fences if you have any values beyond that. Let me just show you what I'm talking about. Let's look at lot size here. And notice I calculated the high and low fence here. Oops. So here it is, the first quartile, the third quartile, the interquartile range is that minus that, right? And the low one is, see, it's going to be the first quartile minus 1.5 interquartile ranges and the high quartile of that. And once again, all we need to do is look at the min and the max. And this is lot size. Now, I can already tell you that most of you already probably know that there's going to be an outlier here. And I'll tell you why in a second. If you weren't paying attention before. Okay, so here we see that 5.4 is the smallest value. That is less than that is more than the low Tukey's fence, right? So no low outliers. But notice that 28.13 is higher than that. So there are indications of outliers in this data. Now, so we want to just figure out, okay, if so, what are they? What values are high? Obviously, 28.13 is a good candidate. That's the largest value, right? Now, if you take our data, let's go to our data here, and I just do insert. Wait, so let's take our lot size. Here's our lot size, and I'll just do an insert box plot. Okay. Just making that a little bigger. Okay. So you see all these dots here? Those are values that are beyond Tukey's high fence. This value here, that's going to be Tukey's high fence. That's going to be 1.5 interquartile ranges above the third quartile. So that's the first quartile, median, second quartile, third quartile here. Let's see if that's true. Notice that there's no dots underneath there, meaning there's nothing below Tukey's low fence. Just to show you that this is what Excel is doing, this is also very common. I'll just do an insert, see an illustration, shape here, and just put a square here. Okay, so there is one interquartile range. Here is two. Did you get that right? Let me make that a little smaller. Okay. One interquartile range, and now I'll take a half. If I put this right up here at that bar, do you see? See, here's the third quartile. I take one interquartile range and see how that's right in the middle, right? 1.5. Tukey's high fence. And so these are listed as outliers because they are beyond that. These do not make them outliers. It's just indication of it. We don't know what the distribution is. We don't know how frequently that are these unexpected or not. We don't know, right? Again, we look for patterns, right? Looking at patterns here, I would say this. I see a lot of values here, right? So do you really think it's that unusual or unexpected? Do these look like they are outlying by themselves? No, I see a lot of value. So they're beyond Tukey's fence, but they really don't seem that unusual. I see a lot of neighbors here, right? So maybe these not outliers. These guys are a little more kind of by themselves, right? They seem more outlying, yeah? And this one definitely way outlying, yeah? So I would maybe consider that an outlier. These ones possibly, these ones probably not. Let me show you another way to look at this that might be helpful, right? Going back to remember our normal probability plot? Yeah? So I've noticed that all those values that were beyond Tukey's fence, many of them, they're right here, right? They seem to follow this pattern very easily, right? So no outlier, right? They follow this distributional pattern, yeah? These ones kind of do, yeah, mostly. I just have a little gap here, so I might not consider. But this one definitely seems unusual. Even if I follow this pattern here, you know, right? It kind of, yeah. So again, this one might be, these one maybe, these ones no, right? So the moral of the story is, even though Tukey's fences are useful for possibly identifying outliers, do not take them as a definition of an outlier. Just like with this normal distribution one, 3 standard deviations, don't take that as a definition of an outlier. Just take it as like, these are things I should look at, right? Yeah? These are things that may be problematic. Okay, any questions on outliers at all? Wow. Any questions on outliers? I'm sure you'll have plenty more. That concludes session 7, right? Yes. So, no, we're not going to do that one. Strike it out. Yeah. Extra credit. You can do it if you want to. It's very interesting, but you can do it. It's optional. Okay, I know you're getting tired. Let's at least get started on session 8. Yeah. And again, remember I said I'm not going to try to make us go any faster, but I do want to use up the time that we have because it's so little, right? So let's make sure we use as much time as we can. And let's move to session 8. Session 8 is on the basics of inferential statistics. So come over here, join me, open up your exercises, and take some notes. It's going to be very basic, I promise, but important that we lay the foundation for what we're going to be working with for our forecasting project in terms of inferential statistics. So I'll tell you that, and by the way, go ahead again just to save us some time, go ahead and download the Excel file for this so that we don't have to. You can always go to the Excel file and look how the calculations were made. Ideally, you would be doing them yourself right now, but that's okay. You know, it's better for us to understand, have this handy. This will save us a lot of time. Okay, so we'll talk about the basics of inferential statistics. So we've actually laid the groundwork for understanding how to infer for doing inferential statistics. Inferential statistics is nothing more than inferring values that we have a sample of data, right? But we're interested in characteristics of the population. That's almost always what we want, right? And so we're going to use the sample as a way to infer something about characteristics of the population. Got that? That's what we're doing. That's what's called inferential statistics. It's inferential statistics because in the population, the characteristics or the parameters that describe the distribution it's not like they don't exist. They're just unknown. We just don't know what they are, right? And so by taking a sample of data, we want to be able to estimate what they are so that we can use those characteristics. That makes sense? So in inferential statistics, there's two things that we do. We do estimation and hypothesis testing. They're actually the same thing, okay? Estimation means that we're going to take that sample data and compute a statistic, right? The statistic is often called an estimator. Why is it called an estimator? Because it's actually that statistic that we compute from the data is an estimate for a parameter in the population. The parameter in the population cannot be computed from the data because we don't have all the data, right? So we estimate it using this thing, something called an estimator. The variety of ways to do the estimation. The estimation that we care about is being able to make a useful estimate. A useful estimate needs to have two qualities to it. One, we need to know how accurate it is. How close is it to the actual parameter value? Because if we don't know that, then it's hard to use it, yeah? Right? If I don't know how good it is, how good of an estimate it is, it's kind of hard to say that, you know, when you make the decision on it, they're like, well, it might be around here, might not be, who, you know, we don't know, right? So that's not a good. So we need to know how accurate it is. We also have to know another thing, because the estimate is going to be made from sample data. The sample data is usually assumed to be randomly sampled, yes? For statistical purposes, that's why we need to assume that. The problem is that when we make an estimate of the sample data, it's possible that just by chance alone, that sample data just was not representative of the general thing. You know what I mean? And so our estimate would be off by a lot more than we would expect it to be. Yeah. So when we make that estimate and we say it's going to be this accurate, we need to know how confident we can be that it actually is within that accuracy. Confident meaning like how frequently it would be within the accuracy that we say it is, right? That would tell us the more confidence we have, the more frequently it is within that accuracy, the less confident, and again, the less confident we are, the less reliable, right? But you'll find that there's a trade-off, there's a trade-off between confidence and accuracy. The more confidence you want, the less accurate your estimate's going to be. The less confident, the more accurate you can be, but it's less reliable because it's not going to be that confident. That makes sense? Yeah. So that's confidence. So in that case, so our estimates, we're going to make our estimates using confidence intervals, which you probably heard of before, right? Confidence intervals just expresses that estimate with a degree of confidence and tells you how accurate it's going to be. I'm going to give you a guy accurate by giving the interval. Hypothesis testing, weirdly enough, is the same thing, but instead of making an estimate, we're going to ask a question about the unknown parameter. The question that we ask is always something arithmetic. Is it bigger than this? Is it less than that? Is it equal to this? Is it not equal to that? That's the only kinds of questions we hypothesize about. And we make a test to check to see how confident can we be that in answering that question, right? That's what it is. And the reason why it's the same as estimation is that, well, we have the sample data, we use that, we make an estimate of the parameter that we're asking a question about, and we use that estimate to answer the question, right? They'll be essentially the same thing. Okay, any questions about that? So I promise you that what we're doing here is nothing more than what we've been doing in previous sessions. We're just going to be doing descriptive statistics stuff, but we're just going to be assuming like an a priori distribution, for example, and then using that as a way to determine whether we get what we expect or not. Or we might be using the a priori distribution to be able to compute the confidence that we might have in something. So for example, the estimation process, again, very simple. We have a population with some parameters that we're interested in that were unknown. Typically, we're often interested in the mean of the population. You know, often we want to know on average or typically what can we expect, right, from something. But that's not known because we don't have all the data. We can't compute this, right? So we take a sample of that data, assuming a random sample. We assume a random sample again so that we do not have bias, right? Right? That's the problem. The problem with non-random samples, I might select things in a way that kind of skew the results, my estimate in a way that's not representative of what all the values are, yes? So I make a random estimate. It also turns out that by making a random sample that we understand the statistical behavior of a random sample relative to the actual thing. It's actually not that complicated to understand, right? Again, there's an experiment that I usually have people do that show you that if you take a random sample, you can actually see what the variability of that sample is as you add more data to it. It follows a very strict pattern, right? You can see it. It looks like this, like a slide, like this. But unfortunately, you get to do that experiment. You'll just have to take my word for it, okay? Okay, so as we understand the statistical properties of random samples, how does the random sample relate to the mean? The estimate is what we can understand statistically, right? And by understanding, I mean we know the distribution for that, and we can use that to be able to determine things like how accurate it is. So we have the random sample, we make a point estimate. The point estimate is that's what we call a statistic, right? Or the estimator, right? So like we just, you know, the mean, we just take the data and sum them up and divide by the number of values, right? Or whatever statistic, whatever estimator we're using, we would just calculate that for the data. And then we use our distributional assumptions to be able to determine the frequency, like 95%, for which the value would be falling within an interval, like 40 and 60 here, right? See, it says mu, 95%, that mu is going to be 40 and 60. Again, this is something we calculate. We calculate what value can I be between. This is going to be in the middle. See, 50 is between 40 and 60, right? So what interval, how long does this interval have to be so that 95% of the time it's actually in that interval? Now, here's what's queer about this, okay? Many people think that this is like a probability. We're talking about this is the probability that I'm between here and here. It's actually not, right? It's not. That's not technically right. For practical purposes, you can kind of think of it that way. But the problem is that the probability that the value is somewhere between 40 and 60 is 40 and 60. That's not what it is. The random value here is not the parameter. The parameter is just what it is. We just don't know it, right? Now, this is fixed. It's not a random variable. So you can't talk about the probability of this being a certain value, right? Because that's not a random variable. There's no distribution for it. It's a parameter of a distribution, but it isn't itself, right? What is random is our estimate, right? We take a random sample. This value will vary depending on what sample I get. So sometimes it's 50, sometimes it's 43, sometimes it's 62, whatever. It varies based on the sample. Every time I take a random sample, I get a different estimate. That will have a distribution, right? That will have a distribution. And that distribution is what I use to calculate that 95% of the time is between 40 and 60. So I say that based on this distribution of the estimate, that the estimate is going to be 95% of the time between 40 and 60 using that distribution there, right? And what happens is that the way this works is that because this is an unbiased estimator of this mean here, that it's always going to be in that interval, that even though this interval may change, but the size of it won't. The size of the size between 40 and 60 won't. So the number 40 and number 60 will vary depending on what this is, right? But the interval will be moving around. So that's the random thing. And the idea is that 95% of the time, that interval that I use will capture the actual value. So it's not the probability of the value, it's kind of the probability of kind of capturing it with the estimate. I know it's a little weird, right? Yeah, I know. But for practical purposes, just think of it this way, that 95% of the time, the actual value is going to be 40 and 60, even though technically that's not what's happening, right? The reason why we need to say it that way is, again, because we have to understand like what method we're using, So the method will change depending on that. All right. Well, we're almost done with this. So let's just do the one problem. So let's just try to finish exercise 1. Maybe we won't. It's kind of a long one, but we'll see what we can do, okay? Okay. So let's look at, so we're going to look at confidence intervals. Okay, so here's our problem. Our problem is this. Now, it's going to seem a little weird, but it's not. You'll see it's kind of more practical than anything else. By the way, I have AI guides for things for doing. So when you're writing these up, please refer to the guidance. It'll help you with these things. So it says, create a new variable called style pool that combines style and pool, then create style pool sheet, unstack style, price by style pool, make plots, blah, blah, blah. All this stuff is already done for us in the Excel sheet. But what we're going to do is style pool. The idea of style pool is we take the style variable and pool, would I have a pool or don't pool, and I just slap them together, right? And I create a new variable, and then what I'm going to do is I'm going to take the prices of homes and I'm going to pull them apart into groups of style and pool. So we had styles, what? Ranch, tri-level, 2-story, right? And then pool, no pool. So I'm going to have combinations, ranch with a pool or no pool, tri-level pool, no pool, and 2-story pool, no pool. And I'm going to look at all the prices. So I'm going to take the prices of a ranch with a pool, prices of ranch with no pool, prices of tri-level with a pool. You get the idea, right? So I split them up into those groups. That's unstacking, yes? Let's go take a look at that. So it says style pool unstacked. And if you want to know how I did it using a pivot table, just go look at this. And there's instructions on here. But you'll see that I have the unstacked data here. See, it says ranch with a no pool. So that's the prices of ranch homes with no pool. Here's the prices of ranch homes with a pool. Here's ones, tri-level, et cetera, right? By the way, I've also added, here are just the homes with no pool. Here's the prices of homes with a pool, all the styles, right? And here's just all the prices, right, of homes. Okay, so the first thing we want to do is, naturally, we have some theory here, right? We're realtors here, and we're interested in selling prices of homes. What would you theorize in principle? In principle, the prices of homes relative to having a pool or not? What would you think in principle? That homes that have a pool, what? Sell for more, typically. Not always, but typically, right? And okay, so we have some reasons to believe that that's true, right? Adds value to the home. What about style? Do you think that style would matter on whether the pool, that price of a home increases with a pool or not? Do you have any, in principle, reasons to think that the style would affect whether the pool or how much of a pool, having a pool has an effect on the price of a home? you're going shaking your head. Right. You should be like, I don't know, right? I don't know. Maybe it does, maybe it doesn't. Yeah, we don't know. Okay, so we're going to look right now. So whenever you do an analysis, we obviously have our theories, right? Want to understand what we have theories and what we expect in principle. And then we always start looking at a visual. We'll always do a visual of some sort, right? So that we understand what we're getting. We don't immediately jump to the statistics because the statistics often will be confusing or might have problems that we need to understand. So we always look to see what we expect, yeah? Okay, so here we are. We're going to look at some box plots. Box plots are a really good way of looking at what the distribution is, and it gives an idea of what the distribution in the population is. Yeah, again, there's only an estimate for these things, but it gives a pretty good idea. And what do we see here? Here's the ranch with a no pool, ranch with a pool. Matches our theory, right? We see that the ranch with pool tends to be higher priced than ones that don't, right? Of course, there's quite a bit of overlap here, which says, it's not always the case, right? But maybe more frequently than not. Here's tri-level with no pool and tri-level with a pool. That's interesting. Well, this does have a higher median, right? And higher mean, but we see that there's a lot of overlap between tri-level with no pool. So it looks like it's lower, but not in general because there's so much overlap here, right? These things like overlap. So it's like, So we have a lot more doubt here, yeah? That here we can be reasonably confident that a pool increases the price of a home. For ranch, here, not so confident, right? Yeah. And then here we see a two-story with a pool. Unfortunately, there was no data for two-story with no pool, right? So we don't know if that matches our theory or not. Yeah. What we do see is that we see that also, here's what's interesting. We see that here's a two-story with a pool and no pool. I mean, here's pool and no pool, right? Pool and no pool. We do see that substantially that no pool seems to be generally lower than pool. Again, a bit of overlap here, which tells us that maybe we're reasonably confident, but not always so. It's not like this one. Like here, look at ranch with a pool, and there's no overlap with tri-level with a pool. We definitely think that ranch with a pool sells for more than tri-level with no pool, right? Very confident, yes. But here we're not so sure, and here in general. Here's also prices of a pool. We could say here's general prices, and we see that prices with no pool tend to be lower, and prices with pool tend to be at typical. And here we see that prices for ranch tend to be higher with a pool, and prices with no pool with a ranch tend to be about the same, right? And then tri-level tends to be lower. So you can think of this as sort of our average, right? Average price of a home. Tri-level with no pool sells for less than average prices of home. Prices ranch with a pool tend for higher than average. Prices with no pool tend to sell for average prices of homes in general, right? Okay, so get an idea what we expect. So what we see here is that our theory about the pool seems to be supported by the data, yes? We didn't really have a theory about the style, but we do see that style does seem to matter, right? In other words, we see that for ranch, it's pretty clear that pool makes a difference, but for tri-level, it's not so much, right? So should we come to the conclusion that, oh yeah, style does matter? No, right? Why not? Because we shouldn't generate theory from the data, right? Because if we do that, the data will always support the theory that we generated because we took it from the data. If we want to support that theory, we'd have to get a whole new set of data, right? And then see if this same thing happened, right? Always remember that, yeah? It's not that it's bad to speculate from the data. You can speculate all you want. Just don't come to any conclusions because the data is not evidence for that. It's only evidence for it when you had an advance idea, yeah? That you had some other principle for that. Okay, so I think that answers this first question. It says, in principle, do we expect that effect of a house to have a price of a home sells? We already answered that. We expected that it would increase, right? Do we expect this to vary by style? We don't know, right? I don't expect it. I do not expect it. I don't know, right? Is there evidence of this from the box plots? Yes, there was evidence from the box plots that including a pool does increase the price of a home. Does it vary by style? Well, it does look like there might be, but we can't conclude that, right? It's not evidence, yes? The box plots are not evidence that it varies by style. It just suggests that it might vary by style. For it to be evidence, we'd have to get whole new data. Is that clear on that? Okay, what else do we have? I promise we'll end soon. And you can discuss the highest and lowest average price. I think we already discussed that. Hopefully you got some notes on that. Okay, so yes, I think we can, if you'd be so kind as just to allow us to finish this one problem. Just get that done out of the way so that we can focus on other stuff tomorrow. Okay, so it says, interpret the 95% confidence interval for the population mean price for all combinations of style with and without a pool. Check whether it's okay to assume the data is normal by getting the skewness, kurtosis, et cetera, et cetera, et cetera. We're going to talk about the accuracy of those estimates. And again, we are now talking about we're talking about the population. We're talking about what are the prices of homes with style and a pool in general, not just for our sample, right? So we're trying to understand what that means. So going to our results here, I think if you go to here, okay, so over to the right. So over to the right on the top here, you see a big table here. All right, so let's take a look at what we got here. We got ranch no pool, ranch with a pool, tri-level no pool. Again, this can actually be computed from Excel, direct, all of this stuff, or Megastat. They'll do it for you. What we care about is we have, I don't like this one. I think I have another one. Do I have another one down here? Damn it. I thought I put another one here. Dab nubbit. All right, well, tell you what. We'll use Megastat to get the whole thing. So here's this table here. See this table of data? I'm going to use Megastat to get it. Now, the one thing about using Megastat or even maybe Excel is that you see ranch with a pool, it only has 3 values. So some of the statistics that we are going to calculate require more than 3 values, right? For example, the kurtosis and skewness needs more than 3 values. So we're going to actually ignore ranch with a pool here because we're not going to be able to calculate the statistics for it. So I'm going to go to Data, Megastat, and I'm going to go to Descriptive Statistics here. And in Descriptive Statistics, I'm going to input everything but ranch with no pool. If you do ranch with no pool, it's going to give you an error, and then Megastat's going to stop working, and you'll have to quit and start again. We don't want to do that. Okay, so what I'm going to ask for it is, oh, what the hell? I'll go get the box plots. I'm going to get the normal curve plots because I want to check normality of the data, and we want, see, it says confidence interval. We want the confidence interval, and we're going to check both Z and T. I'll explain what those are. And then we want skewness or kurtosis. Okay, you guys got that? Okay, and then hit OK. Probably a good time to hit save. And here we are. All right, so let's just do some stuff first. I'm gonna okay, so we have before we interpret the confidence intervals, right? And the confidence intervals, again, it's going to tell us how confident we are that the actual mean price of a pool with it, or price of a home in this style with it without a pool, is going to be between a certain value, right? We're going to want to calculate. First, we need to determine which confidence interval should we use, right? Because there are different confidence intervals that you can calculate, and then we're going to probably want to calculate the error for those. Okay, so the most common confidence interval that you can calculate is that we're estimating the population mean, right? And so we would probably like to use the Z confidence interval. The Z confidence interval assumes the normal distribution of the data. And again, we'll just check to see if it's okay. Not that the data is normally distributed, but is it okay for us to use that? Also, the Z distribution will assume that we know the standard deviation. Now, there's a problem with this, is that if we're trying to estimate an unknown mean, the standard deviation is also unknown, right? And, you know, so assuming that we know it is going to be, you know, kind of hard. Now, we can assume we know it. It turns out that we can assume we know it at if we have a large enough amount of data, right? So if we have like more than 30 data points, then we're able to estimate the standard deviation usually pretty accurately enough where we would say it's known. Okay, and so it turns out that for calculational purposes, that turns out to be just as good as using what the other interval. That if we can't assume that we can estimate the standard deviation well enough, or that it's not known, which is usually the case, we would use the T distribution. Now, why the T distribution? Well, the T distribution also assumes the data is normally distributed, right? But it takes into account that we are estimating the standard deviation. And when we estimate the standard deviation, it adds additional variability. That additional variability makes our confidence intervals larger, right? Because we have to make them larger to account for that variability, which means our estimates are less accurate. So the most accurate confidence interval will be the Z, but if we can't use the Z, we would use the T, which would be less accurate, but it would be more reliable because it takes into account this additional variability, right? Does that make sense? So when we say something is 95% confident, we want to know that it is reliably 95%. We don't want to say, well, it might not be, right? We really want to be 5%. That makes sense? 95%. Now, there are going to be cases where we can't use the Z or the T. So in other words, if we can't assume the data is normally distributed, we can't use either of those, and we'd have to resort to a different way of calculating the confidence interval. Okay, we'll do that tomorrow. I just want to do we'll just do a quick check of these guys, and then we'll call it quits, okay? Sound good? So let's make a little list here. Let's just say normal, okay. And then we're also going to say large data. And then we're going to say reliable. Okay, so let's do the large data first. That's easy to do. For the large data, all we need to do is just check, do we have more than 30 data points, right? And so anytime we have more than 30 data points, we'll say yes to large data. So ranch with a pool, large data, yes. Tri-level pool, no. Tri-level with no pool, no. Tri-level pool, no. Two-story with a pool, no. Close, right? No pool, no. Pool, no. Oh, yes, 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 and yes, right? So for these guys, if we have a choice of using the Z or the T, we'll use the Z if the answer is yes. Why? Because we'll get a more accurate estimate. More accurate means the interval will be smaller, right? More accurate means that we'll be more confident in our decisions, yeah? We'll be able to delineate things more clearly. Okay, now we're gonna see if it's normal okay. So remember for normal okay, well, the easiest thing to check is our skewness or kurtosis, right? Yes? So what was the rule that we would look for? That if the skewness or kurtosis were between -1 and 1, right? Then we'd say, yeah, it's okay, yeah? So between -1 and 1, no, but it's only a little bit. So what should we do? Let's go look at the normal probability plot, yeah, and see if maybe there's an outlier. And if there's an outlier, we're gonna be, yeah, it's okay, right? So let's go back. So we go to, this is ranch with a pool. Look at the normal probability plot. Here's a normal probability for ranch with a pool. Does that look like a line? Sure does, doesn't it? The only thing that doesn't look like a line is this guy here is a little bit of an outlier there. That's probably what's causing our kurtosis, right? If you're really worried about it, you can add a trend line and put look at the R squared, which it's over 0.9, we're fine, right? So we're gonna say normal okay by normal probability plot. It's okay, right? Yeah. How about this one? Is this normal okay for tri-level with no pool? Yes or no? Who said no? Yes, right? You meant yes. Yeah, I know what you meant. You meant yes. So normal okay, yes. What about tri-level with a pool? No. Well, wait a second. Should we go to that, jump to that conclusion? No, we should go look at the normal probability plot, right? Yes. So going down to the normal probability, what was this? Tri-level with pool? Here's tri-level, two-story with pool. Tri-level with a pool. Here's tri-level with a pool. Okay. Test for the day. Last hard thing to think about, okay? What did we say we look for here? A line, right? Is it liney? And we look to see if there are outliers that might be causing it, yes? All right. Do we see a possible outlier here? That one, right? Yeah. So if that weren't there, does that look like a line? Mostly, right? Yeah. But what about if we don't remove that, then I see a pattern. Do you see a pattern? It's kind of a U. See the U? Yeah? And so if we had more data, we're not sure that's an outlier. If we had more data, maybe we'd see a pattern. We went up there, yeah? Maybe we would, maybe we wouldn't. Okay, so the problem here is we just don't know, right? We don't, if it was an outlier, then we'd say, sure, not a problem, right? But if it isn't an outlier, it has this pattern, it would be a problem. So because of that, we're going to be forced to being more conservative and say, I don't think it's okay, right? We don't have any, we have some doubts here, yeah? So let's just say it's not okay to assume it's normally distributed. It wouldn't be reliable for us to do that. Do you agree? would not be reliable because we can't really determine why we're having this issue. Yeah. How about two-story with a pool? Normal, okay? Yes, no? Yes. And how about this guy? Maybe, right? So what should we do? Go look at no pool. Okay, looking at no pool. Oh my God, I don't have a problem with this, right? I see an outlier here, but other than that, it's really straight. I don't see a pattern there. Do you? Right? So I would go ahead and say it's okay. Plus, we have a lot of data. Oh, this is no pool. So no pool, we'll just say yes by normal probability plot. Probably an outlier. Pool has this skewness kurtosis is a little higher than that, but we have so much data, this is not going to be a problem, right? But we'll go ahead and look at, what is it, pool? Pool. Yep, looks a little curved, but not pronounced. Looks like I have a couple outliers there. So yeah, I'd say, oh, fine, right? We also have a large amount of data. Yes. And then how about this guy? Probably the same situation. This is all prices. Okay, looking at all prices. So that was all prices. It's almost the same as with a pool. So same reason. It's okay. So again, just because I'm out of -1 and 1 doesn't mean I would go ahead and say, see, yes, see, by NPP is okay, and here, yes, by NPP. Okay, so we're all okay with that. And oh, sorry, this is the wrong thing. Yes, I put that in the wrong place. Okay. All right. So so that concludes. I'm going to only interpret the confidence interval for one. You guys can do the rest on their own. They're all done the same way. Okay. The only thing that we have to do is determine which confidence interval we're going to use, the Z or the T. If we can't use the Z or the T, we'll resort to something else, but we won't do that now. Okay. So here, let's go for the ranch with no pool, right? We have a large amount of data and we can assume it's normally distributed, right? So we're going to use the Z or the T. Which one? The Z, right? Okay, so here's the Z. And while we're here, let's go ahead and calculate. See, it says the ARMO here. Oh, wait a second. I already had this all calculated. How funny. That's weird. All right. So it says the ARMO, this is the relative margin of error, right? I guess they're always in the output tab here. So we have the relative margin of error here. See, it's 2.44, right? The relative margin error. The margin of error, by the way, here's the interval. 95% confidence, right? It's going to be between that and that. The margin of error is just the upper minus the lower divided by 2. It's called the margin of error because the estimate's right in the middle, right? And the range is between here and here. And so I could be half the time I'm above that, half the time I'm below it, right? So the error or the margin of error would be half the size of the interval, right? Because it's right in the middle. That makes sense? I could be as much as this or as low as that. So the relative margin of error is just taking the margin of error and dividing it by the estimate, right? Saying relative to the error, how much, relative to the estimate, how much error. So this is off by 2.3%. Notice that if this is the Z, so this is the Z here, here's the t. If we are calculating the t, notice the t is 2.44%. It's larger. So the t has less accuracy, right? But that's because I can't assume the standard deviation is known, and so I have to account for extra variability in that. Does that make sense? So I'm going to interpret that one. Now for the rest of it, it's the same way. So I'm going to interpret it here. I'm going to say with 95% confidence, that's the amount that we computed this confidence interval on, right? The population mean price of ranch with a pool, right? Of ranch style homes with a pool will fall within 307, I'll say 307K, $307,000 and 322. That's it. That's our confidence interval, right? And we know how accurate it is. Got a relative margin of error of 2.3%. By the way, I'm sure you've seen the idea of relative margin of error before. Like when they do polls, you know, like surveys and polls and things like that, they'll often talk about what's the margin of error, and they'll say what percentage. That's what they're talking about. And usually it'll be at 95% or something like that. You know, they should say what percentage it is, but 95% accuracy at this error. Okay, now, of course, you should do the same thing for tri-level with no pool, tri-level with pool, and, you know, all these other ones. And unfortunately, I'd switched over from what we calculated to this stuff here, but that's good enough. You guys get the idea, and I think that's enough for today. So tomorrow we'll do C and D and finish 2. And we'll probably call that all for session 8. And we'll probably start working on FP2 and FP3, and that's the end of class. So we have a big day tomorrow. Don't worry, it'll be fun. Oh no, we need to do session 10. We need to do session 10. We'll finish this and do session 10, then FP2 and FP3. What? I think what we're going to do is we'll do session 11 by doing FP3. Yeah, we'll combine them. Yeah, unfortunately, we just don't have time to do a separate session 11. But session 11 and FP3 workshop are almost identical. Okay. Good. Long day. But you guys survived. You did good. I feel good. We're in a good place. We'll finish up tomorrow. Don't worry. Goodbye out in Zoom land.